presented by Page Wizard Games, Learning and Entertainment. It's that time, everybody. Time for more entertainment and fun with your favorite computer scientist, Dr. Daniel Page. Welcome to Dan Plays, where Dan has fun with friends and we talk about all sorts of fun things, including computer science and everything under the sun. No barriers, just fun. Check out all the fun rewards and supporter access at the links. That's enough for now. Let's get started. Come on, Dan. Let's get started.
Hello everybody! I hope everyone's having a beautiful day. I want to welcome you onto the stream here today. I guess one other thing I also have to mention is that it's our first live stream for 2023. If I didn't have a chance to tell you, sorry, I'm getting really excited here, especially about our topic today. But I hope you're having a wonderful new year so far, and I want to wish you the best for 2023. So a couple quick things before we get started. I just want to tell you what we're going to be doing here today, and then we're going to get ourselves into everything. So I'm really excited about that, as I already alluded to. But before I do, today we're going to be talking about strings, and then I'll build up to talking about a concept we call a language. So this is what we call a formal language. And you'll see that this is actually a rather simple concept. And we're going to connect it up to a concept called a computational problem, in particular something we're going to call a decision problem. And then we're also going to be talking about, as suggested in the title, deterministic finite automata. If you're wondering, and I'll mention this again just because it's important, is the singular for automata is automaton. Automata is a plural. These are, if you might be familiar with the concept of a finite state machine. So this is where you have a machine that transitions from one state to another, and there's a finite amount of memory. So we're going to be talking about these mathematical objects. I know I've brought up the M word, the dreaded M word, the mayonnaise. Is that the word? But anyways, so that's what we're going to be focusing in on today. So that's plenty of stuff we're going to discuss here today. And I wish everybody a beautiful day so far. And another thing I need to mention before we get into everything is later today I will be posting the notes from today's live lecture. So if you're wanting to look at those notes or you want to walk over everything we did here today, they'll be available on patreon.com/pagewizard. There's other ways of supporting the work to access these notes as well. If you have questions about that, just feel free to ask, okay? Beyond this, I encourage you to check out patreon.com/pagewizard. It has all sorts of rewards over there, ranging from access to our Discord server, access to these notes, and depending on what tier you're in, you can get your name in the end of every one of the videos that I put out. Likewise, you can access to all sorts of other educational materials I have, early access, and you get a piece of word and saying what we're going to cover here today. So obviously I take a look and see what people are talking about, but most certainly it gives you a voice to say, Dan, I really would like if you could talk about this one thing. This is an excellent way to approach the Patreon. So that's specifically at the supporter access and above. So there's all sorts of rewards over there. I encourage you to check it out. And other than that, I encourage you to hang out in the chat. We're going to have ourselves a good old time here. We're going to be talking about all sorts of fun concepts, and I'm hoping that I'll be able to bounce some things back and forth here today, because we're going to be talking about a lot of concepts, and I need to make sure you understand those concepts before we can really kind of build on top of them to talk more about kind of this general theory around languages and these ideas around these abstract machines. So just to put it in context for what the topic is of today, so this topic is going to be sort of it's an introductory theory of computation lecture. So you're going to find that for those that are inclined to think about finite state machines or think about bits and bytes and things like that, you're going to see that this is kind of like a theoretical counterpart to a lot of those types of concepts if you're familiar with computer systems. So if it looks like there's something very similar going on, that is not a coincidence. It is that likely those ideas are baked from these ideas, or they were developed around the same time. Well, particularly these ones most certainly a lot of them came earlier, so I must stress that. But that's sort of the thing that's interesting about theoretical computer science, is that a lot of the ideas that you learn in theoretical computer science, they will coexist with whatever technology is out there, but they never, especially if they're held to a standard for which we provably we provably state something is true, meaning that we give a mathematical proof for it, it never becomes suddenly wrong, it just becomes a part of the theory. So that being said, only better theory comes along, and that's the only thing that sort of outdates it. So a lot of the theory we're going to be talking about today, I would argue, is rather fundamental for talking about formal languages, and in particular talking about abstract machines. So to understand what a deterministic finite automaton is, for example, it's a good step in the direction of understanding how we could play with a machine without ever having to physically build it or implement on a computer. We could talk about it and compute it as if we were just on a piece of paper, for example. And you can implement it on a computer if you wanted to. Point is that you can. It is not needed at all. But the point is that we're going to be talking about all sorts of topics around this. And again, I'm hoping and looking forward to talking to you about this. So for those in the chat, I guess one other thing I need to mention before we get started. I did mention this on the social media. So if you aren't following me on LinkedIn, Twitter, Facebook, for example, do check out my social media links. If you aren't, I do post updates and every once in a while discussion points for things. But most certainly, you'll know, and probably if you're familiar with like Twitch, because we do stream on Twitch, is that there may be some technical issues going on Twitch. So if you are having issues with viewing this on Twitch, I have the stream is going on YouTube instead. So just please, if you're over there and you're just having issues, please just come hang out over here. The chat is live over here on the YouTube, or if you're watching this somewhere else, more the power to you. So anyways, let me know in the chat how you're doing today. And I can't get excited enough when we talk about this stuff, because I will say this just as a little bit of a preface to this, is that I find that the delineating line between the type of people that would be talking about this discussion you have like people talk about like, oh, state machines and all that stuff. They think of very much about programming and developing software and stuff. This is definitely the line on the other side of this discussion. Is that coming from Twitch? I think it might be coming from Twitch. Twitch is working. Okay, that's great to hear. That's actually good. That's good. I'm glad to hear that. So if anybody's over on the Twitch, I'm happy to hear that. Excellent. One other thing. Oh yeah, before I get too excited about this, I should mention that the chat is indeed live. Let me actually just pull up the chat right now. So whenever the chat is visible on the screen, certain venues will have text-to-speech enabled, so I can hear it. But also I should mention that it's not on the screen, I can still hear it, and I also can see it. The chat is actually right there. So you're part of the audience, so just keep that in mind. So if you want to have yourselves a good old time there and you want me to see something, just put it in the chat. Sorry, I'm just going to drink a little bit of water here. I'm already worked up already. But let's get into this, okay? That's enough of me just rambling on about things. So if you have questions, or you have some fun thing you want to tell me about, or there's some interesting thing, or maybe I missed something. Sometimes that does happen by design. So please let me know in the chat. That stuff is really helpful for me. And it also engages and ensures that everybody is participating, because remember, it's not just the lecture, it's our lecture together. So let's get into things here, because I got plenty we're going to be talking about today. So a natural place for us to start. So today we're going to be starting off by talking about some basic terminology for formal languages. Namely, we're going to talk about some basic terminology around strings. So some basic terminology. So I'm going to hope that you'll have fun and join me in the chat by bouncing some of these concepts off with me as I ask you questions. So please join in the fun. So before I can talk about what a language is, I need to make sure that everybody's kind of speaking the same language when it comes to the different, well, there's that M word. What is it called? It's Is it mayonnaise? Mustard? Either way, it makes a good sandwich. We need to have some terminology to help us understand what we're going to be talking about here today. So the first place I'm going to start is with the concept of an alphabet. Now, I'm not talking about alphabet soup, although that can be pretty delicious, okay? But an alphabet is a finite non-empty. That just simply means that this has to be a collection of symbols. Empty set. So set is just a collection of symbols. So it can't have no symbols. That's all it means by saying it's non-empty. And it has to be finite, meaning that you can imagine it like I have a bucket. So I have a bucket, and inside of here, if I peer into this bucket, I can see all of the symbols that I can use. For example, I have a typewriter. I may have all the alphanumerical characters along with some punctuation. Those would be my alphabet, for example, for a typewriter. Maybe I would include, say, some arithmetic symbols in there too, but anyways. So often we use the symbol capital sigma, which I'll just colloquially refer to as sigma, just to keep things simple here, for alphabets. So if you ever see me write down the symbol sigma like that, and not in the context of adding things, but in the context of talking about strings, just assume I'm talking about some alphabet. So let's talk about some examples of alphabets. So for example, I could say that sigma consists of two symbols, 0 and 1. So what kind of set of symbols? Sorry, I'm getting really worked up about this. But if you could think of, if I were to type on a keyboard or type some symbols down and they're just zeros and ones, what would I refer to that as? Like, what are zeros and ones? What are those? So just to give you a heads up, for example, if I had 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, that's decimal, right? But what's it when I just have 0 and 1? Starts with a B. Starts with a B. Binary, yeah. So this is actually what we'll refer to as the binary alphabet. So this is the binary alphabet. Very good, very good. Let's see. Chat's on this, okay? So I can also, now keep in mind, you don't have to use capital sigma to declare the alphabet. I could give it another name. For example, I could call it capital A. This, for example, could be the set of all lowercase letters in the English alphabet. See what I did there? So this could be the set of all lowercase letters. Just as an example. There's another example. Let's think about another one. I could, for example, have it where, coming back to my example talking about, say, a typewriter, or you can think of it like a keyboard. You could have a valid set of characters or symbols that are used to write out a message. You could have it where sigma, for example, could just simply be the set of all ASCII characters. So that would be, for example, all the characters on your keyboard or symbols. So all of these are examples of alphabets. So the point is just it's some non-empty set of symbols. Just to be clear, actually I have a question for you. Just to reemphasize this definition. If I gave you a set that looked like this, there's nothing in here, otherwise written as this. This is what we would call the empty set. Is that an example of an alphabet? So is this an alphabet? So just to make sure we understand this definition. So it's a finite, non-empty set of symbols. Well, no. This isn't an alphabet, right? Because it's empty. These aren't, keep in mind, these are both the same thing, but most certainly they are not alphabets because they are empty sets. They don't have any symbols in them, right? The point is the alphabet has the symbols we can use to write out what we're going to refer to as strings. So what's a string now? So now we're going to build up to a string. So what's a string? It's, for our purposes, it is a finite sequence. And I must stress that you can define strings to be an infinite length, okay? So just for now, we're just going to think about a string as a finite entity. A finite sequence of symbols from some alphabet. Right, that's not too scary or anything, and quite intuitive. You can imagine I have my bucket of characters or symbols I'm allowed to use, and what I do is I pick out those and I can almost look at them like stamps I can put down and press on a piece of paper. And whatever I get out of that alphabet is a string. So, for example, if I wanted to have, let's just do an example. So, for example, 110010 is a binary string. Why would I call it that? It's because it uses symbols from the binary alphabet, right? So that's an example of a string. This is just one using the binary alphabet. Likewise, I can also have another one. I can, for example, write down kitty cat. So kitty cat. So this is a string, right? And it's using the alphabet A. It also technically could use the final example alphabet as well, like this one here too as well. So are there any questions so far? I think this is pretty straightforward, right? You can imagine I want to write out a string. String is just a sequence of symbols, and they're just from some alphabet. So you have an alphabet, and then from that alphabet you can construct strings. So as long as we understand what an alphabet is and a string is, we're doing pretty good. Is everybody good with that? I think we're doing okay. Make sure you show some love in the chat. So, happy. Welcome on in. So, now that I've defined what a string is, remember it's a finite sequence of symbols. So that means that I can go over to a string and I can count the number of symbols it has, right? So that allows me to define something that we're going to refer to its length. So the length of a string, x is the number of symbols in x. Which we will denote as follows. So whenever I want to get the length of a string, I'll just write it with vertical bars on each side like this. You might be familiar with this. If you're familiar with a little bit about set theory, you might be familiar with that be indicating size or cardinality. So the same translates over here. So let's do some examples. I think that's a pretty natural place for us to go. So as an example, suppose I give you a string that just has 0. So there's one symbol, right? This is a binary string. It just consists of a 0. What's the length of this string? Can somebody tell me what the length of the string is? What's the length of that string? And I must stress that these are vertical bars. They're not ones here. It would be 3 if these were ones, it would be 3, but right now I just want to talk about this one. 1, yes, it's 1. I should be clear, and I should be very careful when I use this notation. And a piece of advice I would give you is if you use this notation, make sure the bars are a bit taller, kind of like I drew right here. But also, if it's unclear, maybe instead of writing it like this with a tick, maybe write it with a little bit more to the 1, just to make it a little less ambiguous, okay? So that's an example there. That's usually my opportunity to bring this up, is try to avoid being ambiguous, okay? So notice naturally I write a 1 like this. But the point is it's not confused with this notation. Let's do another example. So just following my advice now. So if I have 1, 1, 0, 0, 1, 0, what's the length of this string? Six. Yeah, see, 1, 2, 3, 4, 5, 6. See, you guys get this. It's very nice and simple. All you do is just count them. It's very intuitive. Just to really make sure we all understand this, let's check out what the length of the string kitty cat is. So all it is just how many symbols are in the string. And I must stress that we're talking about counting these. We're not talking about the number of distinct characters. That's a different concept, right? Because the number of distinct characters would be counting how many unique characters there are, as opposed to how many there are. So we care about how many there are. So what's the length of kitty cat here? And remember, there are no spaces or anything. Because remember, a space could technically be a symbol. At least if we're using ASCII. But remember, my example, I used the alphabet A. Yeah. Very nice, very nice. Now this is where it gets a little bit fun. Because I've talked about having strings, and I said it's finite, right? But I didn't say anything about the possibility of a string that can have no symbols, which is technically possible. And this brings me to a concept called the empty string. So we have the empty string. So this is an interesting but important concept. It's simply a string with no symbols. It has 0 symbols. And we often denote it, and I must stress that different authors will use different conventions for denoting the empty string, but commonly you'll find that it is denoted as lowercase epsilon. So it's the Greek letter epsilon. So this is epsilon. And I must stress, we have to be very careful here, that epsilon, the empty string, is a very special symbol because it isn't technically a symbol of any alphabet, right? It just represents the empty string. So the empty string, so string epsilon, is not a symbol, in an alphabet. So just please remember this. When somebody writes down as epsilon, it's not a part of any alphabet because it represents a string with no characters, right? So please, if you're wondering what this would represent, and say if we're talking about, say, programming languages or anything like that, you may be familiar with it looking like this. Like where in a string you might denote it with double quotes. Say it has no symbols. That's an example of the empty string. So that's what epsilon is, if you're familiar with that concept. So just remember, it means there are no symbols in the string. It's not the same thing as me saying that it isn't, like, this is denoted with a symbol, but it is itself not a part of an alphabet, okay? So it's a little weird when you first think about it like that. Is that clear, everybody? Is that the empty string is just a string with no symbols. In programming languages like Java or C++ or languages that will use double quotes to denote a string, it'll just look like two quotes like that with nothing in it. But it's still nonetheless a string. Now, once we have strings, we can start talking about sets of strings. So we can describe sets of strings. So you notice that we're sort of building up to something here. That's not a coincidence, okay? So now I want to talk about a few bits more of notation and another concept about strings you might be familiar with if you've heard of strings before. Like I said, I'm really starting at the basics here. It's just that we're formalizing these concepts. Okay. So now that I've defined what a string is, we know what a string is, I want to talk about different ways we can have sets of strings. So I'm going to mention that and also an operation we might use on a string. So some common ones. So some common ones include the following. So each of these all have their own special symbols to talk about it. So we're going to first talk about the idea of powers of an alphabet. And I must stress that this concept easily generalizes. So I could talk about an alphabet raised to some power. So just like you have like a number and you raise it to an exponent, you can do the same thing to a set of strings. And namely, you could even do it to the alphabet itself. So what does that mean when I do this to the alphabet? It's going to be simply the set of all strings, of length k. Of length k, where all the symbols come from the alphabet, right? So let me give you some examples of what I mean by this. So if I gave you the binary alphabet, so remember the binary alphabet is just simply the set that contains two symbols, 0 and 1. So if I give you the binary alphabet, then I can write, then if I gave you sigma squared, so I'm squaring this right here, it says that this is the set of all strings of length 2 from the binary alphabet. So what you do is you just simply take the symbols and you write out all possible strings of length 2 using these two symbols. So for example, I can use 0 and I can use 0 again. There's a string. I can write 0, 1, I can write 1, 0, and I can write 1, 1, right? These are all strings of length 2 using these two symbols. So it can use all zeros, it can be all ones, it can be a mix between the two. So that's, for example, sigma squared. So yes, you can square the binary alphabet. So anyways, let's do another example. You might ask, okay, so what is sigma raised to the power of 0? So when you're staring at this, you're like, okay, sigma to the power of 0. Now, if we're talking about arithmetic, like numbers, very often you just presume, oh, something to the power of 0 is 1, right? But remember, that's not necessarily how this definition works, right? It says the set of all strings of length, whatever that is. So what's going to be in this set? And I must stress that a set is just denoted here with these curly braces around the objects inside of it. So what we call the elements of that set. So what is this then? So what's going to be right in here? What's inside of here? So let's look at the definition. It says the set of all strings of length 0. I talked actually about this just a moment ago. What are all of the strings of length 0? How many of them are there? How many strings are there of length 0? How many of them exist? Is it 0 or is it 1? 0 is a pretty good guess at first, but remember, we just talked about an idea that there exists a string that has no symbols, right? What did we call that? What was that? What was the string that had no symbols in it? Close. It's not the empty set, it's the empty string. Empty string. So remember the empty string? That's epsilon, right? So that means that if you take any alphabet, you raise it to 0, it's actually just a set containing epsilon, the empty string. So, but the reason why I say that's a very good guess, because it's a very common mistake that people make when they start thinking about a set that contains the empty string. So I will clarify this. So note that this is empty set, which is a set that contains no strings, right? It has nothing in it. Has no strings. So the empty set is actually not equal to the set with the empty string in it. Why? Because the empty string is still a string, right? How many things are in here? 0. How many things are in here? 1. The empty string. Does that clarify that? So this is just some examples of using this notation, and I thought it would be a good opportunity to kind of distinguish the difference between a set containing the empty string versus the empty set. So another concept, and it's related to what we just defined here, is we call it often I'll call it often sigma star, but it actually has another name as well. In fact, it has a couple different names. So it's sometimes, so this operation is sometimes called Kleene star or Kleene closure. I'll refer to it as Kleene star. Now you might ask, what the heck is a Kleene? If you're wondering where that comes from, this is actually the name of a logician that actually did he developed a lot of the theory actually I'll be discussing at some point if I talk more about theory of computation. In fact, we'll encounter a theory of this logician's name, Stephen Cole Kleene's name. So this is the name of a logician. So by today's standards, a lot of the stuff that he was doing was what we would call today computer science. But a lot of pioneering computer science was logic. So, well, specifically mathematical logic. So, anyways, let's define what this is. So, I must stress that this is often written like this. So, you have the alphabet, and you raise it to a star. So, some will just abbreviate this as using a star operation on this set. So, instead of it being a number, it's just a star, okay? An asterisk. So, this is the set of all possible strings. the set of all possible strings, whose symbols come from sigma, the alphabet. So just to be clear, what that means is a way you could define sigma star is as follows. So sigma star is actually the same as me writing as follows. It is all the strings of length 0 using the symbols in the alphabet, combined with, so I'm going to use a union operation. It's just simply going to mean I'm going to dump all of these strings into one super bucket, which is a set too. So I'm going to lump these all together. So I'm going to take all the strings of length 0 that use the alphabet. I'm going to take that and combine it with the set of all strings using the alphabet of length 1. I'm going to combine this with the set of all strings of length 2 using the alphabet, and so on. So a question. Is sigma star a finite set or an infinite set? So you can clearly see that for some fixed number, so k, this is indeed going to be a finite set, right? But is this a finite set? Is sigma star a finite set? It's infinite, right? Because remember, it's all the ones of length 0, all the ones of length 1, all the ones of length 2, all the ones of length 3, all the ones of length 4, all the ones of length 5, all the ones of length 6, and so on and so on and so on, right? And remember, the alphabet is non-empty, meaning that there is at least one symbol in that alphabet, right? That set has at least one symbol in it. So it means that if you're considering all possible strings of a given length, it has to be some combination of the symbols in said alphabet. And that's at least one. So if I'm enumerating an infinite number of these, each one is going to have this, none of these are going to be empty, right? Excellent. As a remark, if we ever want to have the set of all possible strings over an alphabet, but I don't want the empty string. There's another piece of notation I want you to be aware of. Some people use this a little bit more often. It's sigma with a plus instead of an asterisk or star. So this is just simply, so this is the set of all strings like sigma star without epsilon. So it won't include this one right here. It will include all the strings of length 1 and up. So just as a remark, I just thought I would mention that. Okay. So that's so these are actually a couple of different sets of strings. Are there any questions about these? Or is it pretty darn clear? I must stress that these concepts do easily generalize over other sets of strings. This is just over the alphabet. But I haven't yet talked really about general sets of strings yet. I just talked about over the alphabet. So if we're okay with this, let's proceed to talk about an operation that we can do with strings. This is another piece of the puzzle, okay? Okay, so now that we've talked about what an alphabet is, we talked about what a string is, I want to define, so I'll say, so it's important that we know how to multiply strings. So how do we multiply strings? In my earlier years, this concept was very fascinating to me, but you might know it under a different name. So you may know this as concatenation. So this is often referred to as concatenation. That's the fun word of the day. So this is where if you have two strings, one is appended, meaning that you attach it to the other one. One is appended to another. So let me be a bit more precise about what I mean by that, in particular more exact about this, okay? It's important that I do that. So just be a bit more precise. If I give you two strings x, and it's x1, x2, x3, and so on, and the last symbol is x sub k1, and y is equal to y1, y2, y3, all the way up to yk2, then to concatenate x and y together, which sometimes people will write with a dot, just to be clear, you can write this. So xy, this is actually equal to x1, x2, and so on up to xk1. And immediately after xk1 is y1, y2, all the way up to yk2. So that's what xy would look like. So if you're wondering, sometimes people will write x times y like this. Hence why I say it's like multiplying. In fact, that convention is very natural. Hello, hello. I hope you're having a beautiful day. Welcome on in. So one thing I do want to bring up, just because I talked about an idea of raising alphabets to exponents, I'm also going to talk about that idea as well when we talk about strings. So to concatenate several times a string x, say n times. So suppose I want to do it n times. We get string x to the power of n. So just as an example, just to really illustrate this, if I have x is equal to the string cat, then that means that x cubed, so this is the same as me writing out cat 3 times, right? Because I raised it to 3. So this is cat, cat, cat. So now I have an interesting question for you. And we've talked about something kind of like this just a moment ago when we talked about a set of strings. What would it be, and this is a convention more so, but it's something conceptually interesting to think about, what would be x to the power of 0 in this case? So if I give you cat and I say, oh, I have it raised to 0. Well, think about it. Think about it in terms of the number of times you're concatenating x. But namely, how many times you're writing it out. I should be a bit more precise. How many times are you writing it out? Okay, if I say 1 time, that's just cat, right? If I say 2 times, that's cat, cat. If I do it 3 times, it's cat, 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 like that. What would it mean to write out cat 0 times? What would it be then? To mean that I give you nothing. But what is that? What kind of string is that? We had a special name for this one. So what is a string that has no symbols. We had a name for this thing. Empty string, yes, the empty string. So I concatenate it no times, as in like I have the string and I write it out that many times. So this is just me writing out, say if I have x cubed like this is 3 times. I write out cat 3 times. If I write out no times, then there's no symbols, right? So just as a fun little exploration of these concepts. So now we're going to get into some juicy stuff. And it's going to sound at first a little strange. So I hope we'll be able to kind of walk through this carefully. So that's the most of the stuff I have to talk about when it comes to strings. But now we're going to build on top of the terminology we built here. And we're going to be talking about another concept, which is going to first be like, oh yeah, that's kind of obvious. Like, what is that? There's nothing really fancy-pantsy about it. It's just a fancy name for something that you can easily describe, right? And that's the best kind of formal thing. It's not very hard to understand. It's just a useful term for something that it's just a common way of talking about it. Okay. So next we're going to define what is called a language. So for those in context, when I talk about a language here, I'm talking about a formal language. So all a language is a set of strings, whose symbols come from some alphabet. So let's talk about, so now you might be looking at it like, Dan, that's all a language is? This is it. There's nothing scary about this. However, we're going to see that this concept, just having a set of strings, unbelievably generalizes another notion in computing that we're going to talk about in a moment. But I think it's important that we see some examples. So let's talk about first the language consisting of all binary strings. So naturally it's over the binary alphabet, for example. It could be binary strings starting with a 1 is as follows. So, for example, I could describe this to you. Now, I could do this more formally, naturally, but I'll just describe it using just a literal description of the set, but it won't include all the elements. I can't list them all because there's an infinite number of them. But notice that these are going to be all strings that start with 1. And that's a language, right? This is just an example of a language, just a set of strings who come from some alphabet. So next, let's talk about the set of all binary strings. A set of all binary strings whose value, so if you interpret this binary string as a number whose value in binary is prime. So I could, for example, describe to you what amounts to the binary representation of a prime number. Now, for those that aren't familiar with what a prime number is, it is simply a positive integer whose number of divisors is exactly equal to 2. 1 and itself. That isn't 1. Right? So it has to have 2 distinct divisors. So for example, 2 is a prime number, 3 is a prime number, 5 is a prime number, 7 is a prime number, 11 is a prime number. I encourage you to think about why those are prime numbers based on what I just said. So I could write out those actually like this. So for example, 1, 0. This in binary, what is that in binary? Now it's not a 10, it's in binary. So you would have, each of these represents a successive power of 2 starting from the left side. So this would be the highest power of 2. So I have 2 of these here, so it starts 2 to the power of 1, to the power of 0. But I take whatever the toggle is on to mean I include that in the running total. So I start over here on the right, to the power of 0, which is just 1. Notice that this is a 0 here, so I don't include that in the sum. Plus 2 to the power of 1 times 1 is just 1 times 2, right? So that's just, so this one is 2. That's 2. The next one is naturally 3. So notice here that this is 2 to the power of 0 times 1 plus 2 to the power of 1 times 1. That's 3. So the next one here is 3. And then next I could talk about 1, 0, 1. So 2 to the power of 0 times 1 is 1. Plus 0 times 2 to the power of 1, that's 0. Plus 1, which is 1 so far. Plus 2 squared times 1, which makes, that's 4. So I add that to my total, that's 5. And naturally, I could keep doing this. So this is actually 7. I'll let you think about that one. But this set is infinite in size. There's an infinite number of prime numbers. So one thing I will acknowledge here is that there's many ways to represent prime numbers using binary sequences. I'm going to presume in this example, as I'm going to do later, that we're talking about the most compact version. We're not padding these with zeros, okay? Why? Because those might represent all sorts of other things. But I'm just going to keep it simple here, and I must stress that you can take that set and you can easily generalize it by padding 2 zeros in any one of these, for example. But the point is that each of these represents a prime number. So just as a fun little note, I will point out here, is notice that every one of these actually starts with a leading 1. So that's actually one of the main reasons why I'm bringing this up. So you won't have any of these, as I've described them to you, ever have a 0 in front at the beginning of the string. So let's talk about some more examples. So sigma star or Kleene star. This is a language. So this is for any alphabet. Now, you'll notice in my definition, I say it's a set of strings whose symbols come from some alphabet. I have a question for you. Is the empty set a language? Is the empty set a language based on this definition up here? So think about it. It just says a set of strings whose symbols come from some alphabet. Now, indeed, an alphabet is non-empty, right? It's a non-empty set of symbols. However, remember that it's just a set of strings. But do you notice that I didn't say that the set of strings is non-empty? So yes, it is a language. Very good, very good. So this is what we would refer to as the empty language. So empty set, empty language, quite natural. Is the empty language. So the empty set is the empty language. And I must stress that it could be over any alphabet. So it doesn't matter what the alphabet is. Empty language, It's a language. So now, this brings me to some interesting revelation. Now, if you've never heard of this before, this might completely blow your mind. And I must stress that when I first heard this, it got me really excited. And this is something that once you kind of see it, you can't unsee it. And this is something that especially when I talk about analysis of algorithms, when we talk about algorithms, I think it's something that it's important to kind of put into the back of your mind. Is that once you start talking about languages, it actually provides a framework for which you could discuss all sorts of different things. Namely, a natural one that you see a lot in theoretical computer science is the idea that you can ask a very simple question about a language. So if I give you one of these languages over here, so does a string belong to a language? Very natural question, right? Does a string belong to a language? You might ask, Dad, why does that matter so much? Well, let me try to frame this carefully for you. More formally, problems, and specifically I'm talking about computational problems. So these are the kind of things you run into when you study computer science. Or for example, if you probably have encountered the scenario I'm talking about in some way, shape, or form. We can have all sorts of fun discussion about it, but most certainly I'm going to keep this specifically limited to certain kinds of problems for the point of our discussion here. Okay? So problems can be defined as languages. So in the world of theory of computation, very often you'll find that people use the word problem and language almost interchangeably. Depending on the class of problems you're talking about, you can use a concept of a language to talk about what a problem is. And once you do it, it just blows your mind. So let me give you an idea of what I'm talking about here. In particular, I must stress that for certain problems, there's a direct correspondence between the idea of a problem and a language. And asking, does a string belong to a language? So I could talk about a problem in a specific way. And I'll talk about it like this. So a problem, so it can be, and I must stress that can be doesn't mean it necessarily will. It's just that it can be. So there's different types of problems out there. For example, you might be familiar with what we call function problems. This would include cases like I give you an array and I would like you to sort the array. So notice that there isn't like a question being asked. It's just, I have my input, now do this to it. You can describe things like that in terms of languages, but I will not focus on that here. Likewise, you could talk about things like optimization problems. These are where you have given an objective function and you have some constraints in place, and you have to decide by computing the best of possible feasible answers, the optimal one or an optimal one. These, for example, could be paraphrased as a kind of what we're going to talk about here, namely what we call a decision problem. Those are the ones I'm going to talk about here. So these can be described as deciding, and I use the word decide very specifically, deciding if a string, which I must stress that these can be binary strings, which in the context of theory of computation almost always is just presumed to be the default, is the binary strings. And you don't lose anything by doing that. I'll let you think about that, or if you have questions about it, you're welcome to bug me about it. I will most certainly answer it. such as binary strings, which we can presume without loss of generality. So there's just a certain step you have to do to convert any arbitrary alphabet to the binary alphabet, or take binary strings of some alphabet and convert them over to binary strings. If you're familiar with encoding strings, say for example ASCII characters, these can represent bytes or sequences of bits, and you can write them out as zeros and ones, like you would on an actual computer, like a tangible one in front of you that you might be watching this on. That's a very natural thing to think about, and that's very much the same kind of reasoning I'm talking about here. So it's nothing too abstract or strange in that regard. So naturally, deciding if a string belongs to some language. So just to be a bit more precise about my language here, so when L is a language, so I'll abbreviate language with lang like this, over some alphabet sigma, what I could do is I could ask a very simple question. Given a string W, which is going to be of all possible strings in the alphabet, so sigma star. So remember, this just simply means all possible strings that over that alphabet. So for example, if this is the binary alphabet, this is all possible binary strings, okay? So all of them are finite in length, but it's all possible ones. Is W in L, so this means in, or is it that W is not in L? So if we can try answering this question for some language, there's actually a natural way of talking about this from a computational standpoint. So this brings me to talking about what a decision problem is. So I'm going to give a formal definition of what this is. You may have heard of what a decision problem is at a higher level. I'm going to show you that that notion is no different than here. So if you've never seen this before, you're going to kind of have your socks blown off. Not literally, but figuratively. Formally, a decision problem, so this is how you traditionally will define a decision problem. A decision problem is where, so what I prompt you with here is actually, my claim is that this is the decision problem, is where for every string W in the of all the binary strings, W has an answer. Has an answer of either yes or no. As let's say not, but we'll stick with no. So for any one of the strings, you can either, for each one, we'll have an answer of yes or no. Do you see how this looks awfully familiar to what I just described up here? Is it in the language or is it not in the language? So let's think about this. Sorry, I get really excited. So the big thing I really want you to notice here is a decision problem is specified as a language. So you could specify a decision problem by a language L, which is going to be some subset of all possible binary strings, where conveniently, this is how we define this, where every string in L answers yes. So all those binary strings that answer yes, they are part of this language. And that language is what specifies the decision problem. So this is one way you can do that. So just to put it all together into a bow, I need to put this all in nice connection for us. So I want you to just kind of just digest what I just wrote there and try to think about the connection between L and what it means for a decision problem to answer yes. And then once you see that, really what we're talking about are languages. At least over all the binary strings, which isn't quite exactly how somebody approaching, say, problem solving from a higher level algorithms perspective may think about this. So I'm going to be addressing that. But first I'll do an example, but let me just make sure it's clear what's going on here. So a string. So once you get the connection between these two things, which is as follows, a string W is in L if and only if, so just for context for those that are aware of what if and only if means, whatever I write over here, if this is true, whatever comes after this also has to be true. If this is false, then whatever's coming after here is also false. So please keep that in mind. So a string W is in L, which is a subset of the binary strings, if and only if W's answer is yes. So we characterize a decision problem actually by the answers yes as a language. So that's actually how you could define what a decision problem can be specified as. It's a language. And what is that? Let's kind of dip in with an example here, okay? So we're going to talk about, because I brought up the set of all binary strings that represent a prime number in binary, let's do an example just to illustrate this point. So let's talk about primality testing. So this is testing if a number is a prime number or not. A very relevant problem for those that are interested in, say, cryptography or number theory. So this is just the problem of testing if a number is prime can be described by a language. Described by a language. What's that language? Well, we alluded to this earlier, but let me write it in a somewhat more formal way. So rather than explicitly trying to write out a sequence of binary strings, I'll write it with what we call set builder notation. So these are all going to be, these are all binary strings. So each one of my strings in this set is going to be a binary string, such that, that's what this bar will represent. This means such that W is a binary representation of a prime number. And we're not talking about padding this thing with zeros, just to be very clear. Now, let's put this within the framework that we just talked about, okay? So let's put it all together in a nice framework. So if given a string W, which is a part of the binary strings, say yes if W is in that language, LP, and no otherwise. So do you notice that if I were to pull up what this language is, it contains all of the binary strings whose representations are prime numbers in binary, right? So whenever I give you a binary string and it is in this set, right? Whenever it isn't, it's not in this set. So just as some examples, just to illustrate my point. So if I give you a binary string 1101, is this in LP or is it not? Let's walk through how we would compute this number in binary and convert it over to something we're a little bit more familiar with in decimal. So let's see. 1, because it's 2 to the power of 0 times 1 plus, okay, nothing for the power of 2 to the power of 1, right? We go 2 squared. So 1 plus 4, that's 5, right? The next power of 2 is what? What is the next power of 2? We have 2, 4, 8. It is a 1 there, so we take our result of 5 plus 8, which this number is what then? What is that binary string actually representing? It is... What is this number? As a number, to be a bit more precise. It's 13. It's very good, very good, everybody. 13. So that means that this is definitely an LP, right? 13 is prime. So if we wanted to consider binary strings like these, we might need more computational resources to determine if they're an LP or not. So it's going to take a little bit more clever thinking to determine cases like these. How about if I give you a binary string that's just a 0 like this? So remember, it's over all the binary strings. That includes this one right here. Is that representing a prime number? And I must stress that we're using a typical representation as per my example earlier when I was defining languages. So for example, the 0 doesn't represent like turning on a switch or something like that. It doesn't. So this would be 0 times 2 to the power of 0, which is just 0. Is 0 a prime number? So remember, this is just 0, right? That's just 0. That is not in this language, correct? That's so in this case, no, because every this is every, let me just every, that says every, it's sort of melted in the microwave. Every integer that is positive begins with a 1. Right? So notice that you know right away this is not going to be in the language. In fact, all strings that start off with a 0, as per our discussion previously, are not in LP. So just as a natural question about this, you can also say by same proxy that 0, 0, 1, 0 is also not in this language either. So I must stress that these are easy to test for. You just see if the first symbol is a 0 or not. And I remember, in our representation of these binary numbers, I'm not including the padding of these. So this reasoning only applies because we're presuming that there is no padding on the binary strings. I could easily change that if needed, but I am not most certainly talking about those types of binary strings. Is that clear, everybody? So these are examples of binary strings that are in the language or not in the language. And you can see that it's the same as me posing a question to you, right? So notice that any one of the binary strings that is a yes answer is in this language. Any one that is not, and that includes that includes all of the junk too, like this one right here. So these cases are not terribly interesting because they're just junk. So please just keep it on the back of your mind. Like pick it up like a feather, tell your little Triceratops friend to say, okay, remember this. Hello, welcome on in. Welcome on in. Hope you're having a beautiful day. Now so is this example clear to everybody? So now we could talk about a decision problem as a language. But please take note that I'm talking still about strings, and I'm talking about them being in a language or not in a language. But they're overall possible binary strings. So I want to really kind of hammer in this idea that really this framework is quite natural even without thinking about them all as binary strings. So let's talk about this. And the main reason why I mention this is because sometimes people ask me, Dan, what does this have to do with like designing algorithms and all this stuff? I think seeing it from a big picture standpoint is very helpful. I remember when I was first learning about this stuff, like sure, there's times when I was learning it myself and then seeing it in a course, I remember it being unfortunately disappointing because we never kind of talk about the big picture of this. Like, how does this fit in to the concepts that we may have talked about maybe in, say, data structures and algorithms course? So how does this all fit together? So you may or may not have seen this in relation to this, if you have. So please remember that this is just still these are all binary strings, right? But they could literally just be strings. So it's maybe useful to talk about a language only in the context of talking about, oh, they're just strings. They're just strings of ones and zeros. But for those that are familiar with computing, you might know that strings of zeros and ones don't just have to be strings. Sure, they're literally strings of binary, right? They're just bits. But they could represent many more things. You could abstract on top of those to mean all sorts of different things. And that's where I'm going here. So while it is sometimes helpful to view languages as only containing strings, which is what their definition is, right? Only containing strings. Only containing strings. Strings can also encode, because remember, there's this idea of encoding things. I could describe things to you, right? Strings can also encode or represent mathematical. I had to use the M word, okay, everybody, I apologize. But if you're not liking the word mathematical, just think of things like a list. If I give you two numbers as input, do something. You can think of an array. You can think of a tree. You can think of a graph. That's what I'm referring to. Represent mathematical objects such as numbers, formulae. So if we're talking about like a logic formulae, like a well-formed formula, for example. Formulae, it could also be even a graph. And this isn't really that strange of an idea, like I said previously. Remember, all the time when we use a computer, at the lowest level, you could think of data as just zeros and ones, right? It's not a strange idea, at least from a computational standpoint, that view computers at these days especially, just as just a bunch of zeros and ones. So for example, if I take a graph and I represent it on a computer, that graph is going to be at some point represented as a bunch of zeros and ones. So the idea is not that alien, at least if you're thinking about it like that. Naturally, those strings of zeros and ones have a length. That's what you would refer to as your input size. right? So for each problem, you define something called the input size. That's the same concept that you talk about in analysis of algorithms, for example. But at a theoretical level, I must stress that the way you encode these objects is very particular and not really for things like unary, which that is a whole other topic that I will not be discussing here, but if you're curious about it, please let me know. Just please be aware that you can take binary strings and they can represent stuff. That's the point I'm getting at. So at a higher level, just kind of take a step backwards, okay? Because at higher level, I'll refer to these as higher level problems. Although this is typically how you would talk about a computational problem in the first place. At least before you would see something like a language like this. So in algorithms, so higher level problems are defined as what? So if you've seen some of my lectures before, or maybe you've heard about this before, maybe in a course you've taken, or maybe you're just curious about this, you might be familiar with a picture that looks kind of like this. Like you have all these problem instances. You have a whole bunch of problem instances. This could be potentially infinite. Usually it is. And we refer to each one of these dots in the circle or weird blob shape. I don't want to prescribe it a shape. It's a sort of weird looking. The point is it doesn't matter. Those dots, when I try to use an algorithm to solve a problem, it has to solve every one of the dots and produces the answer every single time, right? Has to produce correct solution every single time. That's what it would mean for an algorithm to solve a problem, correct? That's a classical way of viewing algorithms and problem solving. So let me just characterize that here now. So in algorithms, problems are defined as a set of problem instances, or just simply instances. Now, if you're not familiar with that terminology, all I'm really saying is that they are the possible inputs. They're the possible inputs. Now, what makes this a little different than just simply what we talked about over there, where we say the input is always a binary string, right? But we said it's any binary string. On the most purest level, an algorithm has to be able to solve the input, like regardless of, it has to be any binary string. That's the most purest way of looking at algorithmic problem solving. So I'm going to show you that actually it doesn't have to feel like that, or does it need to be like that? That's the point I'm getting at. So watch this. Where the form of the input is explicitly defined by other mathematical objects other than binary strings. Like it's just not just a string, it's just defined by other mathematical objects. By other mathematical objects. Not only, and I use this, I'm using this at a higher level, okay? So I'm not saying that these are not encodings of binary strings, I'm saying they're not just any arbitrary binary string. That's what I'm getting at. Because sometimes when you encode these objects into zeros and ones, they may not actually have always a corresponding binary string. So if I go through and enumerate all the possible binary strings, some of them are actually not going to represent some input of my problem. That's the point I'm getting at. That's kind of the gap between these two things. So I want to address that for you. So not only a string from or in, I'll just say in the set of all possible binary strings. So we can adopt the same definition the same definition for decision problem here as well. So please just, this is sort of my way of saying, even though your input won't always be some arbitrary binary string, at a higher level, what we're doing is actually the same thing. That's what I'm going at. Okay? So let me just explain here now. And I must stress, this isn't the only way you can go about this, okay? So this is just one way of thinking about it. But I must stress that they're all things you can just sit down and actually prove through very, I would argue, relatively simple arguments. Using all the terminology we've talked about up to this point. So, remember, when we talk about a problem in this more abstract or higher level sense, you could, for example, be talking about like a decision problem of a different form. For example, it could be given an array A and a key X or a value X. I want to know if X is in the array. Notice that has a very specific form. What you would do in that case is you can imagine each instance of that problem as a string of zeros and ones for which each one of the elements and the value X are encoded in binary. So every one of the instances will have its own encoding. And once you view it like that, then now the decision problem is actually specified by all of those instances that are encodings of arrays and with a value for which the answer is yes. So that's how you could frame this framework we just talked about, where you specify all the yes answers as a language. But traditionally speaking, you would have it where you have the ones that are like yes, and the other ones that are the answers no. But the point is that it still fits like a glove into this other framework that we just talked about here. Because remember, and like I mentioned, it's going to be a little weird at first. But the point I'm getting at, let me just summarize what I just said in broader terms. Define an encoding, which I'm not going to refer to this so much. I'm not going to tell you what the encoding is here. Just take my word, at least in this lecture, when I use the word encoding, I'm just saying you have your instance. Like we think about like the search problem, or if we talk about primality testing, you can imagine I'm taking that and I encode it as a binary string. Define an encoding that takes each instance of your problem, each instance, and represent it as a binary string. A binary string in the set of all binary strings. So you're defining a way of encoding this information into just pure bits, right? And this isn't a strange idea. It's very intuitive, right? This is what computers do. This is like your computer isn't literally, when I give you two numbers as input, it doesn't, when it's processing instructions, it isn't just literally saying, hey, look, these are two numbers, now do the thing. That's a very high level way of looking at this. It's actually an abstraction of what we're talking about here. It's just, you encode the instance as binary. That has a length, by the way, just in the exact same way I defined length of a string earlier, right? So that's, hopefully I'm connecting some dots for you that are they're very much there. But I'm not talking about how the encoding happens, because there's different encoding schemes that exist. Some do not provide theoretically the framework that you would like to for if you're thinking about analysis of algorithms and computers. Other ones create encodings that are very, very long strings that are not going to represent things that make a whole lot of sense. Namely, I'm pointing at you, Unary, somewhere over there in the corner. But that's a whole other topic for another time. The point is just that this exists. So whenever any binary string, so remember, so I can imagine I have each one of the instances I can represent as a binary string. So this is just a conversion. So the encoding defines a function that's going to take each one of my instances, translates it to some binary string. Now, there's going to be binary strings that actually don't map with any one of these encodings. I referred to them colloquially earlier as junk, and that's how I like to think about them. Whenever any binary string in here does not correspond to the encoding of an instance assign its answer. And I'm going to do this for convenience purposes. There's several other ways we can address this issue. I'll maybe mention a few here. Well, actually, I'll just maybe mention one or two. I think this is one natural way that most theoretical computer science would be pretty content with to know. So what does that mean when I say that every one of these other ones are no? Well, what does that mean? They're not in the language that corresponds, that specifies the decision problem. That's what I'm getting at. So all of those strings that are not in the specified by the language, those could be the junk ones. They could also be no answers. So just be aware that there's sort of an asymmetry here. Now, I did say I was going to mention another way of thinking about this. Is another way that some theoreticians would go about this, and it's quite common in something called reductions, is whenever you have something that does not actually fit what exactly the desirable instances you're interested in, what you do is you define the encoding so that there is a way to take any one of the ones you don't care about. You make them into what we call canonical or non-canonical example, depending on what context it is. You consider a fixed instance that you map all of those onto. So for example, if this was a graph theoretic problem, what you would do is any one of the ones that don't represent a graph, like if you take the zeros and ones, they aren't a graph, for example, you just presume that they're going to be mapped by some encoding to be representing an empty graph, for example, which in that case it would be a trivial no answer if it was something else more specific, like computing a path from A to B. In that case, an empty graph would never have an answer for that. It would be something very easy to check. Just like our example when we talked about primality testing, when I had the leading zeros, I could have easily remapped all those instances so that so if I gave you an integer like 0 or a negative number, actually not negative, but the point is if it was a 0, I could map that to represent 1 in binary if that was needed. Or, sorry, I should be a little bit more precise. The 0 would represent the integer 1. And it's okay if they map to multiple instances like that. But the point I'm getting at is that once you have this in place, you could assuming that it's easy enough to determine what these junk instances are, you could think of it just like what we talked about before. That I give you the thing, as long as I could check the input, and it's easy to do, very often, and this is something we do all the time in algorithms, is we just presume we're given the input as desired, just like in this higher level way, and it follows the exact same framework we just talked about. So the instances, so when we talk about our problem, the instances of our problem, so we're talking at the higher level here, that have yes answers are called yes instances. And instances that have no answers are no instances. So the big thing, the big kind of revelation with all of this, just to be very clear, is that every time you're looking for a yes instance, the two notions match exactly. That's the point I'm getting at. So observe that answers for all instances of the higher level problem and their binary encodings. They're encoded binary strings as per what I described up here. Encoded binary strings match. So the big point I'm getting at, this is the big takeaway of all of this. So regardless if we adopt the more formal, I should put more in parentheses because I would argue that when people think about problems, they often are given formal definitions, but this is more formal. It's even further lower level from a theoretic standpoint. The more formal definition, or the higher level definition of a decision problem, it captures the same correspondence, right? Namely what? It's that if I get a yes answer, that is a part of the language that specifies the decision problem, right? And that's true regardless if you're talking about encoded objects that can be in turn encoded into binary strings. And all of those instances that answer yes, they will be a part of the same language. Even if I considered all binary strings. Hopefully that's interesting. I think this is I'm trying to explain a very interesting abstraction issue here. So please take in mind that what I'm doing is I'm showing you that if you learn about decision problems, say like just an algorithm design course, I'm talking about the same concept. As opposed to a theory of computation, more formal, I don't like using that phrase because they're both technically formal, but this is more formal, more lower level. These are the same things. Just please remember that once you go to this broader case of inputs, sometimes it is the case that the encoding always has a binary string. Sometimes it may not be, but the point I'm getting at is that there's a way to deal with all of these junk instances whenever that is the case. So hopefully you thought that was interesting. So I thought I would show you an interesting framework for which, one, what a language is, and two, a connection among others between languages and decision problems, and how you can relate that to a higher level version of talking about decision problems. So really when we talk about language, it's really the same thing, right? In fact, many times when you talk to somebody that studies algorithms or theory of computation, they'll use the word language and problem almost interchangeably, depending on which one's more useful for the conversation. For example, if we're talking about just specifically the strings and something about those strings at a lower level, they might use the word, the researcher may use the word language. Or they may, at a higher level, what they're talking about, like we talked about here, like just a problem, thinking about just trying to solve it, they might think of it at a higher level because the way I describe the problem to you depends on objects that are described to the person as input, and I'm expecting some output. In this case, we're talking about yes or no answers. Fascinating stuff, right? Are there any questions? Any questions at all? Don't be shy. This is a good opportunity because I will tell you that when I was doing my studies, I didn't ever had somebody ever lay this out for me. And I think it's a very helpful thing to see. Like the connection between the decision problems and language, most certainly, it's a very classic connection. But very often I find that unless you really dig into a good course on algorithms, this lower level view of decision problems versus the higher level, sometimes this jump is sort of just presumed. And I like to be upfront with you about it. Because it is a subtle one. Because notice that classically we define the input as just any binary string. As opposed to just, oh yeah, here's my input, I give you two numbers. It could be the case that the binary string doesn't have a valid encoding. We would call, for example, what I talked about as junk. These would be invalid encodings of the objects. So very often, like I said, you could, for example, just presume any one of these, because remember, to come up with this observation is to prove that there's a correspondence between these binary strings and the instances. And what I was saying during the lecture, our discussion here, is that all of those binary strings that are junk, you could just simply say, those are all just no instances. And you namely point at an instance. You just point at one and you say, hey look, it's just this one. They're no different than this one. And it's okay to map multiple instances like that in the context of binary strings versus instances at a higher level. Hopefully that is, I just think that's interesting, is that there's this direct bridge between these two concepts. And all we did was talk about strings. We haven't talked about like really advanced problems, but the point I'm getting at is that a decision problem can be extremely, like the framework we're talking about is an ever-encompassing framework, and many problems can be described within the context of decision problems. And I thought that seeing that would be rather helpful. So I thought before I get to my next thing I wanted to point at, I wanted to summarize one last thing, just to kind of put the nail in this. Just because I think it's important you see it up front so you have an idea where we're going with a lot of this stuff. Is that there's kind of two ways you can view a lot of what we talked about, at least. Is solvability, as in, does there exist a way for me to test if some string's in a language or not? Solving some decision problem, in that sense. And efficiently solving the problem. So, in the higher level framework that we talked about over there, something like that might be helpful to think about, but keep in mind you could also talk about the first thing too. Namely about solvability. Can I solve the problem? Does there exist an algorithm that does that? And you could think about the algorithms that was abstract machines. So for example, when you talk about pseudocode and all that stuff, there's sort of a presumption that there is some machine that can understand this pseudocode. So I must stress that you have a model of computation for which it can understand the pseudocode in the same vein as, say, if you have a programming language, and that programming language is what, when you use a compiler, it translates it over to some lower level code to some degree. Eventually that is some machine code at some point. And that is something that it will be read by the CPU to perform and carry out instructions if we're talking about like a physical digital computer. But my point is that you could still talk about the same exact things without ever having to touch a computer. That's where I'm going with this. You could talk about an abstract machine that does this. And you could implement these ideas. So just to summarize our last point. So in summary, is that it is possible to describe any decision problem, which I must stress that decision problems are normally framed as questions. Akin to my examples. For example, I give you a binary string, and I want to know, is the binary string in the language. In that case, does it have a is it representing a prime number in binary? That's a yes or no question. Likewise, you could talk about search problem. At a higher level, we talked about the idea that you could encode the array and the values, and you could ask the question, is X in the array? So it pertains to some part of the input. You'd ask, it's a question, right? Yes or no. Describe any decision problem as a language and vice versa. That's the big thing I really want to hammer in. As a language and vice versa. So we can use these terms interchangeably. So somebody talks about a problem, talks about language. In this context, they're the exact same thing. Just sometimes, like I said, a language, you can think of it as a lower level thing involving specifically strings, but as soon as you start talking about input and problems at a higher level where you're encoding objects, it may be more useful to use the phrase decision problem more explicitly as opposed to just language. Pretty nifty stuff. Let me just erase the boards here, and then we're going to be moving on to our next topic. If you have any questions at all, please let me know. Actually, I want to make sure I identify what marker that was, because I always have markers in my pocket, and I think this is the one. I'm just going to put this one aside, because the next topic we're getting into is a lot of fun. But I hope everybody's having a beautiful day so far. Just as a reminder, if you're looking for the notes for this lecture, they'll be available afterwards. So later today, I'll post them on patreon.com/pagewizard. So if you want to see these, including the examples, they'll be on there. And they're available as low as the supporter access tier, which is just simply, it's like magnitudes cheaper than taking a course, okay? So it's meant to be very affordable. So if you're curious about these topics, you want to learn more computer science, everybody's welcome here. So, what was it? One other thing. One theme for this year that I really want to get people excited about is that I really want to make it clear that right now our project here is to try to build something outside the university system. So if you want to learn computer science and you want to find an alternative way of learning computer science, or you want to enhance or boost your learning, well, say if you're studying a computer science program at a university, what I'm doing is I'm developing something in the long term that will be something along these lines. So please consider supporting academics outside of university, such as myself, so we can continue doing our research, even though we are not currently within that system for reasons that are unfortunate. So please consider doing and supporting the work that I do here. Put a lot of work into these lectures. And at the same time, I'm hoping that you find the lessons that we're taking and doing here valuable. Excellent. So I just had to mention that. I will have a proper video discussing some of these things coming down the line. So I will be discussing these things at some point. If you're curious about any of this stuff, just please reach out to me. I'm always happy to talk about all sorts of things. I think it's a part of the academic tradition to be able to discuss and explore ideas regardless of if they're taboo or not, if they make someone upset or not. Just try to be decent to others. That's all I really have to say. It's one of those things. I know we have a fun time here, but I think it's important that people know, like, hey, look, to pursue truth in its most beautiful form, it means that all ideas have to be on the table, even the ones that people don't like. So, anyways. So previously we talked about languages, we talked about strings, we talked about what an alphabet is. We talked about all these concepts building up to languages. We talked about what a decision problem is. But we haven't said anything functional, as in the sense of trying to solve or decide if we're in a certain language or not in a certain language. Question. I'm in Canada. I'm in Canada. I'm in the Great White North. But no. We were, what was it doing? But yeah, no, I'm near Winnipeg. So if you're looking for me, I'm around Manitoba. So I live in Sunnyside, Manitoba. It's a place just outside of Winnipeg. But yeah, no, where was I going with this? Yes, now I remember. So we have ourselves this concept of a language, and I would like to know if a string is in a language or it isn't in a language. Now, for those that are in tuned or learned a little bit about computation before, you may be familiar with the idea that I want to come up with a procedure for which I could decide an answer to that question. And this brings me to something that's quite natural if you think about computers, is think of a machine. Just to kind of put it all together, just as a basic example. You may be familiar with an idea of a finite state machine. If not, that's okay. Oh, awesome. Everybody's on welcome here. We have ourselves a blast over here. So you can imagine I have a switch. It turns on or off. It has two states. It has an off state and an on state. And imagine I have a machine that can turn on the switch or turn off the switch. It has two possible states, and to do that requires me to transition from one state to another state by flicking a switch. A very basic, simple machine, right? So every time I toggle the switch, you can imagine this as describing this as whenever I'm in the off state, if I toggle the switch, I go to the on state. If I toggle the switch again, it goes into the off state. And so on. So you might say, Dan, that's an awfully cute little schematic of the flow of how a switch would work, right? It turns on or off. I could toggle, and imagine this is just a button. It could just simply be a button press. So very often people could design schematics for machines based on little flow diagrams like this. This is actually what we would call a transition diagram. It is based on a graph theoretic concept called a directed graph with self-loops. So I have labels on these different states, and I could transition from one state to another. Now, sure, this is cute, right? Like, it describes a very simple machine, a switch. However, suppose I wanted to know something more than just, oh yeah, it's a switch, it turns on or off. But I wanted to answer an ultimate question about this design here. Suppose I wanted to know what sequence of toggles will ensure that when I'm done toggling the switches, that it's always going to be in the on state. So imagine that whenever you get me the switch, it's always in the off state when it starts off. So suppose I toggle the switch. So if I toggle it, so just as an example, if I just do one toggle, it's in the on state, right? However, if I toggle, and then I toggle again, it goes into the off state, right? It goes toggle, toggle. I just follow the arrow with my finger. So I toggle it, it turns it on, toggle, it turns off, right? But if I toggle, say 3 times, so I go toggle, toggle, and then I toggle again, suppose this is a sequence of actions that I do. I end up back in the on state, right? Well, if you think about it, I could describe a sequence of toggles, these toggles, as a language. And suppose that each of these toggles is actually a word in my, it's part of the alphabet. So each time I say a toggle, it is like I turn it on or off, right? But what if I wanted to describe a language? So suppose I wanted to describe a language describes all actions that leave the switch on. So do you see that if I were to try to answer that question, that every time I press the toggle, and I do it an odd number of times. So notice if I press it once, it gets me on. If I go sec 2 times, 3 times, it goes back on. 4 times, 5 times, it goes back on. Do you notice that if whatever that language would be, is whenever I give you a sequence of toggles, that's always an odd number. Do you see that? So do you see how even when I describe a very simple machine like this, if I give you a sequence of actions, which we can think of as input, I can read that input as a sequence. Toggle, toggle, toggle. When I finish reading this, I should be able to know if it's in the on state or the off state. And I could even describe a language, perhaps we're going to talk more about this, of the ones that leave the switch on, just as an example. So this is me motivating the idea of a finite automaton, or finite automata if we're talking plural. So this is an example of an automaton. You might know this as some people call it a state flow diagram, some will refer to it as a state machine. Either way, these are all manifestations of the same idea. But that brings me to talking about what I just described to you. Okay, we're going to be describing a machine that its job is to decide if a string is in a language or isn't in a language. As in, we're going to decide if the input belongs to a language or not, and we want to design the machine such that it will recognize a given language. Now that's going to be the framework we're going to work within. Is that clear, everybody? So let me describe this for you. So how a finite state automaton processes strings is by reading the input string. This is the convention we're going to pick up, is reading the input string left to right. Left to right. So you're going to imagine you have some input that's provided to this machine. Let me draw a fun picture to kind of put what we're putting in place here. So you imagine I have my machine, my finite automaton. Here's my machine. And this is the framework that we're going to work within. And I must stress that by adding features to this machine, we can potentially decide more languages by recognizing them, right? But what we're going to talk about are just finite state automatons. So they means that they're going to have a finite number of states, just like I have 2 toggles here, like two possible states I can toggle between. They're also going to have a couple limitations as well. So let's talk about that now. So this is kind of the big picture. So you can imagine that the input is provided as a string. And you can imagine it's like a piece of tape that's fed into the machine. If you've ever seen something called ticker tape before, it's kind of like if you imagine the tape's getting loaded into the machine and it starts right on the first symbol of the string, starting on the leftmost side. So you can imagine it reads in tape like this. Now, I must stress that this is just a picture. It doesn't have to look like this. So imagine I give you a string W as input, and it's going to be read from left to right. So it's going to be pulled through here, and you imagine it's on this tape. And the finite automaton has a reader. It has a reader. And it starts on the first symbol in the string. And what it will do at a high level is it's going to read each one of the symbols on the string, and it will react based on what the input is. So this will mean it will transition from possibly one state to another state. And what would be desirable is whenever I give you a string W, that when I finished reading the string, that it's sitting in a state for which it will tell me if it belongs to the desired language or not. So just like I was talking about, which strings would give me, or you think of these as strings, which ones would leave me in an on state versus an off state. It's the same thing here. Just it's a little bit broader. So you can imagine, this is a figure showing you what one of these finite automata might look like and its capabilities. But it doesn't have to literally be this. It's going to have actually a formal definition. So this is just a high level view of how this will work. So let me just summarize this. So given a string W, which is going to be x1, x2, all the way up to xn, the DFA, so if you're wondering what a DFA is, I'm going to define this in a moment, but it's a deterministic finite automaton. You'll see what I mean by deterministic in a bit. The DFA begins in an initial state what we'll call conventionally Q0. It doesn't have to be called Q0, it's just the name we're going to give it for our definition. Then, based on what we're going to call a transition function, which we're going to define in a little bit. A transition function, which this will define how we go from one state to another state, just like on our example here, where I say, to go from the off state to the on state, you have to toggle. Just in the same vein that when I want to go from the on state to the off state, you have to toggle. So this would be defined by this so-called transition function. This transition function, and we'll call it delta, lowercase delta. Sorry, no, not delta. Yeah, lowercase delta. Delta. I get my symbols sometimes a little mixed up. I'm just having a little bit of fun about this. Symbol x1 is read and based on what x1 transitions to, it transitions to another state. And so on. So what will happen is x2 will be read next, and then it may potentially transition to another state, and so on, and so on, and so on. And then finally, xn is read. So let me just maybe put a number on this. 1. Then there's stuff that happens in between. Then there's finally xn is read and may transition to another state, right? And if the DFA, I'm just going to make some more room here, and if the DFA is in a state that belongs to the final or accepting states accepting states, it accepts. Otherwise, it rejects. So I don't have enough room there to say, but it's otherwise rejects. I'm going to define this all in a moment. So I'm just trying to give you a high-level picture of what we're going to be in for when we talk about a deterministic finite automaton, or plural deterministic finite automata. So there's this notion of acceptance and rejection. So it either accepts or rejects W. So it's got to do one or the other. It can't do something in between. It has to do one or the other. So let me now define what a deterministic finite automaton is. And remember, it doesn't have to look like that picture right there. It doesn't at all. It's a mathematical, there's that dreaded M word again. It's like mayonnaise or mustard. It makes good sandwiches. It's a mathematical object. But the point is it's still a machine. It's an abstract machine. It's an example of what we call an automaton. It's an abstract machine. It's a type of model of computation. Given it's all of its faults and great things it can do. Deterministic finite automaton. Which, this is a DFA. So whenever I refer to a deterministic finite automaton, I'll refer to it as a DFA because it's a bit of a mouthful to say that every single time. So one thing I need to point out is that DFAs, they aren't just simply just some model of computation. They also can be used for all sorts of different things. So many practical applications use these types of objects or equivalent formulations of these things for things like string parsing, for doing types of what we call Lex analysis, and also all sorts of other problems as well. I mentioned, for example, you could, for example, test a circuit using formulations like these. But there's many equivalent ways to define the languages that can be recognized by one of these DFAs. So let me define a DFA with you, and then we're going to do some examples so you can see what it's like. We could play around with it. We're going to design some DFAs, and then we'll see a bit more from there. So hopefully you're getting a little excited. I know I am. I know I'm very excited about this. But I will warn you, at first this is going to look really intimidating if you've never played around with mathematical objects that have more than just two pairs, or a pair, like a graph or something like that. This is going to look a little intimidating, but I assure you, there's nothing scary about it. It's very intuitive. Just think of our picture over here. So it's going to be a quintuple, or a five-tuple. It's going to be, I'm going to call it A, but remember this is just a name for this DFA. It can be called whatever you want. It's going to have 5 parts to it. Q, capital Q, sigma, that you might recognize as an alphabet. Delta is the transition function. Q0, we said that was the initial state, and we're going to have what we're going to call our final or accepting states, F. So this is our set of states. This is the set of accepting or final states. So let me just lay out what all these are. So Q is a finite set of states. You might ask, Dan, why is it called a finite automaton? Notice that there's a finite possible number of states here. It's the first dead giveaway. Next, sigma is a finite non-empty set of input symbols. So notice that we're talking now about input symbols, and it will remind you just of the definition of an alphabet, right? Next, we have delta is a transition function. This is going to be the tricky one for me to define for you, but once you get it, it's not too bad. Is a transition function. It's a transition function. Let me just switch markers here. I'll give you a moment there. So delta is a transition function. So delta is the name of the function, just to be very clear. That takes as inputs slash arguments, whatever you would like to call them, as inputs or arguments, a state. So it takes a state and a symbol. And a symbol. Then returns a state. So you give me, what, Miss Kitty? What? Yeah, I know, we're talking about DFAs. What do you think, Miss Kitty? Yeah, no, Miss Kitty, the transition function, it's going to take in as input a state. Yeah, exactly. Yeah, a state and a symbol. And then it's going to return back a state, Miss Kitty. Yeah, exactly. So, more formally, how you would define this is as follows. So the fancy way of writing this down, more formally, delta is a function that takes a state and an input symbol, and it outputs another state. That's all this says. Right, Miss Katie? So that's what a transition function is. We're going to see examples, so don't worry if this looks a little daunting. Don't worry, it's all good. So remember, this is what's, just like in our toggle example we had over here, its job is going to just simply say, I give you a symbol that's going to be read. I'm going to transition to another state. So I have to be in a state at that time, right? Every time I'm executing, I'm in some state. That's the point. You're in a current state, you read a symbol, then you tell me where to go. That's all this says. If you want to think about it as a lookup table, that's a very intuitive and very perceptible way of looking at this. Next, Q0 is one of the states. So it's among the states Q is the start state. So there is one state that is dictated as the start state. So this is the state the machine begins in. So if it doesn't read anything, it just is in the start state. So once this starts up, it's going to go from the start state to potentially other states. Then finally, F, which is going to be a subset of the states, is the set of final or accepting states. So either one is fine to say. It's pretty common to use either one or the other. So the point I'm getting at is that when the DFA reads the input, it transitions from state to state to state, but each time it will gobble up one of those symbols and when it's reading it. So this tape is you're gonna imagine like tape going through this machine, and when it's finished reading the input, it's gonna tell you an answer. It's either gonna say accept or reject. We say it accepts if the state that I'm presently in at the end of reading out that input is in F, then we accept. Otherwise, we reject. So I'll have a more formal way of talking about this in a bit. But for now, I think it's a good idea we see an example. I sort of left everybody over here. Come on down. Come on. Let's go this way. So I thought it'd be a good idea. You see an example where I just use the definition directly. So that way we're not talking at a higher level or anything like that. We're just sticking directly on our definition. And then we're going to see ways we could describe DFAs in other matters. you're going to see that there's at least a couple helpful ways to do this as well, other than the formal definition. So let's do an example. Suppose DFA M1 equals the following. So as S0, S1, S2. So remember, the first of the 5 tuples is the set of states. So these are our states. The states are S1, S2, and S3. Sorry, S0, S1, S2. Sorry, getting really excited here. Then we have our input symbols. Then we have the transition function, which I'm going to describe below this because it takes a little while to frame it. Then we have S0. S0 is going to be the start state. So the DFA is going to begin in S0. And the final or accepting states is going to be S0 and S2. So these are our final states. Where, now I'm going to define for you the transition function. Where, now remember, the way this works is that I give you a state and I give you an input symbol and you have to tell me where you're going. So if I'm in S0 and I read a 0, then the DFA is supposed to go get into a state S1. If I'm in S0 and I read a 1, I go to S0. If I'm in S1, state S1, and I read a 0, go into S0. If I read an S1 and I read a 1, I go to S2. Next, if I'm in state S2, I read a 0, I go to state S1. And finally, if I'm in state S2 and I read a 1, M1 goes into state S1. So this is a complete description of the transition function. Note that you have to define every one of these. Otherwise, you have not defined the transition function. The transition function here is required to have it where you give me a state, you give me an input symbol. So you have to define for all possible states and all possible input symbols where you're supposed to go. So notice, and the reason why it's deterministic is notice that whenever I'm in a state and I read a symbol, it goes to exactly one state. They can't go to a set of states, for example. That's a whole other concept that we're going to talk about maybe sometime in the future. So remember, that's the set of states. This is the input symbols. This is a transition function. Please note that for every state there is an input symbol. And that means that all of these are defined. You can't omit these unless there's some construction you have that tells you what you're supposed to do in all other cases, okay? And finally, these are our final states. So S0 and S2 are the final states. Now, let's talk about processing different strings using this definition. So please, let's follow carefully this process. So I'm going to do this at a higher level. So I'm hoping that you understand how this is going to work. Okay, remember, you're going to start off, you can imagine the reader is on the first symbol. And every time it reads a symbol, it's going to pull that tape just one over to the next one, and it reads that one. Each time it'll perform a transition as per the transition function. And when we finish reading the input, it'll either accept, so M1 will either accept or reject the input string. So let's do an example. So suppose W, the input string, so suppose that the input W is the following binary string. It is 1, 0, 1, 0, 1. So it means that when we start up, we're going to be in state Q0, and we're going to begin by reading this 1. So first, it begins in S0. So what's the first thing it does? It reads a 1, right? It reads the first symbol. It reads 1. But if it's in state S0 and it reads a 1, where's it going? Where's it going? What is the transition table? Well, sorry, our transition function. I'm getting ahead of myself. This looks awfully a lot like a table. That is not a coincidence. It's a very meaningful way of thinking about it, like I said. But remember, I'm in S0. I read a 1. It says to go to S0. So we're staying in S0, but we're transitioning there, right? Then we transition to state delta S0, 1, which is S0. Now, we finished with 1. Now let's read the next symbol. Next symbol, we read 0. And we transition to state, which state? We're in S0, right? We read a 0. So we're in S0, we read a 0, it says to go to S1. So we're in state S1 now. Read the next symbol. We're going to read a 1 next. So we're going to transition to the state dictated by the transition function. So right now we're in S1. We read a 1, right? So we're going to appeal to this one, which says that S1, when I read a 1, is equal to S2, right? So now we're in state S2. Well, M1 is specifically. Next, we read the 0. You read 0. You transition to which state? You transition to state dictated by the transition function, S2. You read a 0, so S2, 0, it says to go to S1. So now we're going to be in state S1. And finally, we read the 1, the last symbol on the input string. You read 1. We're going to transition to state delta. And right now we're in state S1. We read a 1. So that means that we're going, so we're S1, you read the 0, no, read a 1, right? Because the last symbol is a 1. We go here. Notice it says it's S2. Now, will the DFA accept or reject? Remember, what's the state that the machine M1 is in upon reading W over there when we're done? It's in S2. So right now, presently, M1 is in state S2. But S2 is one of the final states, so does it accept or reject? Accept, reject. You only can do one or the other. Accept or reject. Does it accept or does it reject? So is M1 accepting or rejecting here? Well, most certainly, it's in one of the accepting states. Accepts. Very good. So finally, I'll throw step 7 up here. Step 7, it accepts because M1 is at or in state S2, which is a final state. So I'll give you another example, now I'm not going to work this one out for you. It's going to be in the notes. But here's another string, 0, 0, 1, 0. if you look at this carefully, if you walk through the same process, so imagine I give you that the input string is 0010. I will tell you that this case it will actually reject. So I want you to take a look and try and go through the same steps using the transition function, and this one will actually reject. So in fact, there's more strings. I've also included some more in here. Some I've worked out, some not so much. 1, 1, 1, 1. I think how many ones do I got here? I was being very dramatic when I was doing this, okay? That's how I live sometimes. So I got, that's not literally, I mean more in an epic way, okay? The cool kind. So I got 7 ones. In this case, it accepts. So I encourage you to try walking through with this example. Also have 3 zeros. It rejects in this case. So I encourage you to try walking through this process with each one of these. In fact, I have some other ones too, but I'll leave those in the notes, okay? So this can be somewhat lengthy to do to describe the 5-tuple description. So this is actually like the formal description of the DFA. So if ever somebody asks you for the formal description of a DFA, they're asking for this. So this can be lengthy to do. So there's actually a couple other ways to describe a DFA. So let's talk about this. I would argue that these other ways are simpler. It's important that when you do it, you're following some kind of conventions that are easy to parse, okay? So just to be clear, this is a formal description of a DFA. So this is a formal description. So if anybody asks you for a formal description, you could do this. But this could take quite a long time if you have many, many, many states and many, many transitions. It may be a more concise, so whenever you see like the infomercials and they say, there has to be a better way, I'm going to try to give you a couple of ways to do this that are a little simpler. So here's a couple other ways to describe a DFA. So the first one, I alluded to this already, is the idea of a transition table. Transition table. So just think of a lookup table. If you've never heard of one of these before, I'll explain. Because that's what it is. It's a lookup table. This is how very often you might even implement such a thing. You might implement it as a lookup table. It's not the only way, but most certainly that's one effective way. I know somebody, especially if you have more of an engineering background, that's probably the first thing you might think of trying to do. So what do you do here? You list all the states as rows and all the input symbols as columns. If given a state and a symbol, the state to transition to where would it be? If you imagine this as states are rows, the input symbols are columns, all you do is just do this, right? You just do this. They're going to meet at the intersection of the row and the column. Transition 2 meets at the current states, row, and next symbol reds column. Just as an example, just so you can see, because I'm going to use the same thing I have over here. So just to make this a little easier for us to do, I'm going to actually write out the table over here, just because I have the formal description here. It'll be a little easier for you to evaluate for yourself if that in fact is the thing we actually just did. So I'm just going to move over just a little bit, that way you can actually see what we're doing. I just want to make sure that you're not feeling like, oh, Dan's just saying stuff again. That I can double check this, although that's how I usually do things, but you get my point, is that I want to make sure that it's clear where this description fits in the table, okay? So as I said, we're going to make a table. So I'm going to make a transition table for M1. So each column is going to be one of the input symbols, and each row of this table is going to be a state. So I'm going to have a state for each one. Each row has a state, each column has an input symbol. I told you it's just going to look like this. It's nice and simple. Now, there's a couple of things I want you to be aware of. First, whenever we label the start state, you have to have a clear symbol for the start state. It's quite common to use an arrow to indicate the start state. This is just a convention. And also another common convention is that use stars on the labeling of these rows just to indicate that those are the final states. So you'd agree with me, the reason why I put stars here, because these represent the final states, because S0 and S2 are the final states. I put an arrow on S0, it's because that's the start state. Now, all I do is I look at what I have here. Do you see how this looks just like, I could just read this off, right? So S0, when I read a 0, that should be right here, right? So I have S1 right here, then S0, then S0, S2, and then maybe down here I have S1. What would go right here? What goes in that spot right there? Just to be dramatic here, let me get my pointy sticks out. There we go. I got my pointy sticks. Okay. So I'm at state S2. I'm given a 0. S2, given a 0. What should go in this spot right here? What goes right there? So we know that, like, I deliberately wrote it out like this so you can see that it will fit right in there. So what's meeting between the rows and the columns? In this spot, right here. Remember, I'm currently in state S2. I read a 0. S2, let's see. Well, let's think. Let's see. I'm currently in S2. I read a 0. Would it be, well, let's see. What does the transition function say? It says that S2, when I read a 0, is S1. So that means that an S1 should go right here, right? Which is what you see over there, right? I had to do that for flair, okay? So the reason why it's S1 is because notice that each row is telling me this is the current state. You can imagine this is the state I am in. When I read a 0, where I meet at the row and the column where these two meet, that should be the output of the transition function right there. See, notice that the output of this would be S1. Likewise, right beside it is S1 too, because when I'm in S2, when I read a 1, that's right here. When they meet together, it's S1 there as well. Hopefully that is clear. But yeah, so this is an example of a transition table for M1. Isn't this a little easier to understand than that? At least it's a little easier to write down, right? It's not, you don't have to write all these deltas and all that stuff. It's a little more concise. So this is a transition table for M1. And notice that I'm not losing anything by describing it like this. There isn't anything lost in the description. Quite intuitive, right? Is there any questions about the transition table? Is there anything, all that Dan is saying weird stuff again? I think I transcribed them all correctly. Okay, if I don't have any questions, so why don't we proceed? Let's talk about the other way, a very common way of representing these. And it will remind you a lot of the example I did with the toggle machine. So I had the machine that just toggled. The second one is a transition or state diagram. So this will remind you a lot of what we just did when we first started talking about DFAs. Okay, so it's going to take a little bit of time for me to describe it to you, but it's going to be very intuitive, okay? So I just need to make sure I lay it out so that we understand all the rules for how we draw these out, okay? Because it's important that we understand what we're doing. So a natural way, a natural is subjective, most certainly, but I'll say that if you could characterize something that you're looking at as a graph, it can often look quite natural for problem solving. So we can ask all sorts of questions about DFAs on a graph, for example. That's what I mean. So for somebody that's a problem solver kind of mindset like me, that thinks about algorithms, it's very natural to think about it like this. So over there, like that is very natural for thinking about it if you just wanted to implement one of these things in hardware or something of those lines. This is much more natural for like a higher level kind of problem solving way of thinking about it as well. Now, both of them are ways, completely valid ways of representing these things on a computer as well. So just be aware of that. Sorry, I'm just getting really excited. Naturally describe. A natural way, oh, instead of saying describe, let's use the word represent. Just to change it up, you know, just add a little garlic instead of salt and pepper. Represent automata. Remember, that's plural. Automata is using labeled directed graphs. Directed graphs with loops. Now, if you have no familiarity with this concept, I do actually have a series on graphs, so you can check out that series if you want to learn more about this terminology. You're going to see it's not that complicated for what we need. I like to think of graphs as fairly intuitive. At least when you talk about them, it's the terminology that sometimes gets people. That is, we can construct a transition diagram as follows. So we're going to have vertices for the states. That's the first thing you need to know. There are vertices for the states. So for each state Q in the set of states, there is a vertex labeled Q. That's the first thing. So naturally, I'm going to need more space, so let's go over here, okay? So just keep in mind, kind of like our toggle example, which we had 2 states, we had a vertex, but now you can think of it as a vertex if you want. Now you can think of that as each one of the states, they have a label that represents that state. Just like if I had talked about my toggle example, you can imagine I have an off state and an on state. That's literally what they're called, off and on. The next, we're going to have directed edges, which are called arcs as short, or sometimes we'll just refer to them as edges. These are going to represent the transitions. Or transitions from a state to another state. So for input symbol X, which is in the input symbols, and state, or potentially states, PQ in Q, because keep in mind you could stay in the same state. If delta Px is equal to Q, then the diagram includes arc PQ. So there's going to be a directed edge from P to Q. So that's an arc from P to Q, and it's going to be labeled with something. It's going to be labeled X. That's the input symbol that got me there. Now, we're going to try to keep this graph so that it is simple in the sense that we're going to allow loops. So it's going to be a simple digraph or directed graph, but we also allow self loops. So it's not technically simple, but it's not going to have what we call parallel or multi-edges in this graph. So the way we're going to handle that is, because you can have it where you go from one state to another, but with multiple symbols, is for simplicity, if there are multiple input symbols, X in the input symbols, where it goes from P to Q with delta Px is equal to Q. This means I'm in state X, state P. Sorry, I'm getting really excited here. I'm just flowing with this stuff. Go from state P, given X, I go to Q. Then one can label arc PQ with a list of all such input symbols. So you just have a list of symbols as opposed to just one. So you can always think of it like each label will be a list of all such input symbols. If you don't like that, you're welcome to turn it into a multi-graph too, like with multi-edges. But you'll find that it doesn't need to go that far. 3. Once you've done this, you indicate the start state. You include an arrow. Toward the vertex. That is Q0, the start state, from no other vertex. So it's just going to be some weird disjointed arrow that just points at this one, okay? You're going to see in the moment. from no other vertex. And finally, you're going to label the final states. So we're going to walk through these steps to build. So we got to indicate the final states. So don't forget to indicate the start state and indicate the final states. Just please don't forget about those. What you do, the common convention here is you double circle. you double circle all final states. Here, let's see. Cute 0. Yeah, Q0. It does sound like that. But let's walk through this step by step, and we're going to build the transition diagram now. So let's build this sucker. So fortunately, I have the transition table just sitting right here, so we can actually use that. And it's going to have 3 states. So I'm just going to get a different marker here, because this one's starting to act a little funny on me. So we're going to have 3 states. We have 3 states. 1, 2, 3. So I have 3 states, right? I have S0. So you might ask, Dan, how do you know to put them like this? It's mostly experience. Keep in mind, there isn't just one drawing of the transition diagram. It's meant to convey information or data about the DFA. It doesn't have to look like this. But the things that do matter when you actually are talking about what it looks like are what the connections between the vertices or states are, and what the start state is and what the final states are. That's what matters. Not the positioning of where the nodes or vertices are. That doesn't matter. So let's look at our transition table over there. So it says S0 on 0 goes to S1. So let me draw an arc. I'm going to label that with a 0. Right, that's what it says to do over there. S0, when it's in 1, when it reads a 1, it stays in S0. So I draw a self loop, and I label it with the input symbol. That would get me back there as per here. So this is actually just the first row here. I know that S0 is the start state, but I'm not going to do that quite yet. I'm not at step 3 yet, but I could technically just label start state now, but I'm just trying to keep this simple for us. Next row. When I read a 0, I go back to S0 from S1. So I'm going to draw transition like this. Right? That's what it says. When I go from S1, I read a 0. Remember, I just follow it with my finger. That's how you know the transition is occurring, just like when we talked about earlier. Next, it goes to S2 on reading a 1. When it reads a 1, it goes to S2. And that's the second row, the last row. S2, it goes to S1, regardless if it's a read a 0 or a 1. So I just say 0, 1. So I just indicate all the input symbols that it transitions from S2 to S1. And that's all of that's the transition function. I've encoded that information into the diagram. So I have so far followed the first 2 steps. Next, indicate the start state. So very commonly, I'll just write start on it just to make it a little clearer that, oh yeah, this is the one this is the arrow I'm referring to. It doesn't come from any other vertex. I usually put start on it, just to make it a little easier to see. I think it's cute, but at the same time, it makes it clear that that is the case. But as I mentioned here, it's just an arrow suffices. Then finally, I got to double circle the final states. Well, S0, remember in our transition table, I said S0 and S2 are the final states or accepting states. So I'm going to double circle them. So I'm going to put another circle inside of my circles. And there we go. That's our transition diagram of M1. So this is the transition diagram or state diagram. So that's the transition diagram. Are there any questions about our transition diagram? Don't be shy. I'm happy to answer any questions. So is there anything about this that I maybe missed? Perhaps I missed something. But yeah, these are two arguably simpler ways of describing machine M1 without having to describe its formal description to you. So there's at least 3 ways I could describe a DFA to you. The formal description using the 5-tuple or quintuple. I could use a transition table like I have behind me, or I could use a transition diagram. Any one of these conveys the same information. So somebody could present any one of these 3 as a way to define for you a DFA. But yeah, that's what a DFA is. So, are there any questions? Any questions at all? So that's what a DFA is. So what we're going to do actually next, but please, if you have any questions, please put them in the chat. I'm happy to answer them. But what we're going to be doing next is we're going to be talking about, I thought it'd be wise for us to do some examples of designing DFAs that recognize certain languages so that you can see how we could do it. And this is going to involve us putting together some concepts. That way we could kind of play around with this a little bit, as opposed to it just being, yeah, look, it's just kind of this thing that exists. It's nice to have this machine that we formally defined. It'd be nice to be able to actually like tell you stuff that we could do with it by doing some examples. I'm just looking at how much stuff I got here. I got actually quite a bit of stuff here. A part of me is wondering if I should actually, technically speaking, only go through our examples and maybe stop for the day after that, because I still have to go through, for this topic alone, I still have to talk about regular operations. Then we'll talk about formal definition of computing a DFA. So the actual formal definition. So you know how I talk about that, like you read the symbols one after the other. There's actually a formal way of describing this. Then once we've done that, we would talk about what the language of a DFA is, as per what I talked about, and how to prove a DFA is correct. Now, I personally think that we've gone through enough things that maybe after we talk about some examples with the DFAs and what a regular language is, I think that should be enough for today, at least. Otherwise, I might give you too many things at once. But we could always come back afterwards and explore those concepts together next week. How's that sound? Does that sound okay with everybody? We still have plenty of things to talk about here, but I think I think we've done a lot of stuff. We covered quite a few things here today.
Yeah.
I think it's way more fun to talk about designing machines than having to think about, like, oh yeah, there's 4 other things Dan is going to lay on us after this. Because I get to have a little bit of fun with you guys when we start talking about designing machines, as opposed to just thinking about, oh yeah, how do we actually prove that these things do what they do? That's a whole other level on top of this. But most certainly, one thing I did not define for you, which I want to define now, before we get to our examples, and I was going to do it before I stopped with my examples, this example here, is I didn't define something for you that it's going to play a big role in a lot of this discussion going forward, is the concept of a regular language. So I'm going to define that for you now, and then I'm going to erase the boards, and then I'm going to then we're going to talk about some examples of designing DFAs. And many times it's going to feel very intuitive, and there's going to be a lot of little tricks that I'm going to show you when it comes to playing around with these things. By no means is this going to be rigorous. That's going to be given more treatment, I guess, next week, at least according to everybody in the chat. Everybody seems to be thinking, yeah, this is a good idea. Maybe we won't need an overblow of this stuff this week. There's a lot of stuff we've gone through already so far. Oh yeah, I was going to define what a regular language is for you. But anyways, we've seen a few different ways we could define a DFA. One thing I did not tell you is what exactly are the languages that a DFA could recognize. So one last definition before we get to designing DFAs. And we'll get more formal about what this means and all that stuff eventually. Is really this. And you may have heard of this term before, but here's one way of defining it. Is defining something called a regular language. So you might ask, Dan, what the heck is a regular language? Well, let me define it for you. So this is one equivalent definition for a regular language. I say already too many things, but a language L is regular. So this is just a name for these types of languages. It's regular if some DFA recognizes it. So that means that you could design or discover a DFA that for every input of that language, it should be able to accept. So it recognizes that input. And everyone that is not in that language, it rejects. So there's many different ways of formalizing this concept of a regular language. Most certainly, as we explore more theory of computation, we'll see that it is actually a rather fascinating equivalency that exists for this definition, but this is one possible way I could define them for you. So the languages for which that are recognized by a DFA, all of those we could call regular languages. But yeah, sorry, I'm having a little bit of fun with this. So let me just erase the boards here. I'll bring you back over here. So as for those that are curious, if you ever heard of something called a regular expression, that is actually very closely related to this concept. In fact, that is an equivalent way of talking about what a regular language is. So I'm not talking about regular expressions today, but most certainly they actually have a relationship with DFAs, a very close and intimate relationship with them. In fact, if you're curious, a lot of these theorems that involve a lot of this stuff, you know how I talked about a logician named Stephen Cole Kleine? That guy, years back, he was one of the first people to identify this relationship between the DFAs and regular expressions. This is back a while ago. I mean, decades ago. So yeah, no. So as long as you have a DFA for it, as long as it's successfully for every input string of that language, it accepts, and all others that are not in that language, it rejects over that alphabet. You've described a regular language. So I'm gonna get a different marker. This one, I swear I gotta go through all these markers. There's so many of them. I hope you're at least enjoying me suffering over here. It's a good old time. It's like going out for hot dogs or something. Let me just grab another marker. I need to go through all my markers here. Just gonna grab a couple more new ones. Let's see here. So let's get into this, okay? So it's going to be important that you guys get involved with this. So if I start asking you questions, feel free to chime in and tell me what you think, okay? So previously we talked about at a high level what a deterministic finite automaton is and how it processes. We gave the formal definition of a DFA. We talked about how it might process a string. We also seen an example, and we also seen how we can represent DFAs through the formal description, a transition table, and of course, a transition or state diagram. So I thought it'd be meaningful for us to kind of go through some examples of designing DFAs and some trickery that I would suggest here or there when we're thinking about these things. And by no means is there like one way to do this. This is arguably one of those fun creative tasks when you design a machine. And this is one of the fun things when you're studying automata theory, when you really start playing around with the machines. And you're like, oh, well, cool. I don't actually have to like physically build the machine. I could just the machine, it works on paper. I can literally walk it through. So I thought we would do some examples, so that way we can play around with this a bit. So let me just getting ahead of myself. Okay, let's start with this first scenario. So for our first example, let's talk about accepting binary strings. Accepting binary strings with an odd number of zeros. So I want us to think about this. Now for those that need to kind of lay out a couple definitions for you, we say a number is odd if it has the following form. So when I'm counting up the number of zeros in the string, it has to be that frequency, how many times it appears, has to take the form of 2k plus 1 for some integer k. So you'll notice quite quickly if you put in k as 0, you'll see that this ends up just being 1. Put k as 1, you get 3. K as 2, you get 5, and so on. So what I want to do is I want to be able to take any binary string, and I would like to know if it has an odd number of zeros in it or not. Does everybody understand the problem? So I want a DFA that recognizes that language. So I've laid out to you a decision problem that we need to come up with a DFA. It needs to accept whenever there's a binary string with an odd number of zeros and reject whenever there is an even number, right? Because that's the other possibility. So I have some ideas for how we might go about this. Now, I don't know if you have any ideas in the chat. Just please tell me if you have any ideas. Let's see here. So knowing that there's either going to be a state for which there's going to be an odd number of zeros and then there might be an even number of zeros, it might be a good idea to maybe have two states. That might be a good place for us to start. Maybe I'll make a picture. Let's make a picture. Let's go with the transition diagram. I think that's a meaningful way we could start with this. And then, of course, we'll see what it looks like as a transition table and its formal description too. That way we can get a grip over these definitions. So why don't we make a transition diagram? Maybe that's a good place for us to start, just because we know how parity works. There's even or odd, right? So I would like to get it so that maybe I start off in some state. And I have two states. I have Q0 and Q1. And I would like it to be that all the binary strings with an odd number of zeros go into Q1. So when I finish reading the input, I want the DFA to be in state Q1 if there's an odd number of zeros. Do you see where I'm going with this? So anything that is not that is going to be sitting in Q0 when we're done processing the string. If it has an odd number of zeros, we want to make sure it stays in Q1. So notice it could either stay in Q1 or it has to get out of Q1. What characterizes that? So you can imagine this. Imagine I have a string. Like this. If I give you a string like this, it has an odd number of zeros in it, right? It has 1 0 in it. But notice I have a whole bunch of ones that come after it. Do those ones matter at all? Yes or no? They don't do anything, right? These don't do anything. So as soon as I'm reading this, so you can imagine this as a process for which I'm reading each one of these, and I'm keeping track if it's odd or even number of zeros. So the minute I encounter another zero, like if another one appeared like this, you know right away, oh no, this better not be in Q1 if that happens. But if another one comes along, oh yeah, I better be in Q1 if that's the case. So do you notice that the ones really don't matter a whole lot? They just don't. So it's just like if I were instead going to just ignore the ones and just read the zeros. But we need some way of characterizing this. Do you see what I'm talking about? What really matters in the string are these zeros, not the ones. So here's an idea. We don't care about those ones, so I'm just going to make it so that no matter which state I'm in, I'm just going to stay in that state if I read a 1. Seems rather intuitive, right? They don't matter. I just need, if I run into them, I better stay in the same state because I'm trying to keep track if the number of zeros is even or odd. Does everybody see what I'm talking about? Yeah. So what happens? So when I start off in Q0, if I read a 0, I have an odd number, right? So when I have an odd number, it brings me over to Q1. If I read another 0, where does it put? Should I still be in Q1 if that's the case? Should I stay in Q1 if I read another 0 upon reaching into Q1? No, right? Right? No, we don't want to stay in Q1 because that means there's an even number. So here's the design idea that I have in mind. So think of me like the Wizard of Oz. I'm behind the cloak thinking about how I could design this thing. So we can have as many ones as we like. But the number of zeros to reach the final state is exactly equal to 2k plus 1. And of course, that's odd, right? Not odd in like me, yeah. I mean like the number. So now I should label these with 0 then, right? And then now I have defined the transition function. So now if you take a look at my string, this is just one example. So this is one possible input, an instance, you could say. So I recommend when you're first playing around with this idea, you take a few strings out, see if it makes sense. And in fact, you can almost go through a process like debugging your machine by just giving it some strings like this. So if I'm in 0, I read a 0 from Q0, I go to Q1, stay in Q1, stay in Q1, stay in Q1, stay in Q1, go to Q0, go to Q1, and I have an odd number of zeros, boom, I accept it in Q1. So I encourage you to take out some more strings and try it out. But let me just make sure I'm clear with everybody. I should define as well this DFA formally. So that way, this is the transition diagram. So I can also define it like this. So I'm going to call this machine modd. It's going to be this one, but it's actually defined like this. DFI modd is going to be equal to Q sigma delta Q0 and F, where Q is equal to Q0, Q1. Sigma, or our input symbols, are going to be equal to 0 and 1, like this. The start state is Q0. And F, the state of accepting states, or final states, is Q1. And you'll find very often, rather than describing all of those delta terms like explicitly, the formal definition you would give delta in its complete form, as per I did. But you can also replace that with the transition table too, right? So I'm going to use the transition table. and delta as in its transition table. Which, now let's draw the transition table. It's nice and small. 0, 1, because those are my input symbols. I have two states, Q0, Q1. Q0 is a start state, Q1 is the final state, so I'm just going to label them accordingly, where Q0 is the start state, Q1 is a final state. I indicate them with the star. So to go to Q0 to Q1, on 0, it goes to Q1. On Q1, when I read a 0, I go back to Q0, right? And on a 1, I stay in my same state. And there you go. There's the transition table. And there we go. So now I have not proven to you that this is a correct DFA that indeed recognizes the language of all binary strings with an odd number of zeros, but I think this example illustrates how you might go about it. Most certainly, you'll notice that there's a few cases here. In fact, eventually I will prove for you that this DFA is correct, but not today, not today. Are there any questions about this DFA? So you could just straight up use this and it will tell you, yes, it has an odd number of zeros, or no, it does not. So I will tell you that it is correct though. Like this is correct. This is a correct DFA for this. It will recognize such a language. I know, right? Some spooky stuff. Now, let's do another example. Let's get another example going. Actually, I have a little bit of a conceptual question. Let's think about, I want to think about something a little different. This is a question more for discussion. Can a DFA accept the empty string? Now, I must stress, the question is actually a fairly broad question. Some DFAs, the answer will be yes, it will. Some, it may not. But can a DFA accept the empty string? Can one? And I kind of answered it for you, right? But why or how? So if ever you needed to accept the empty string, there's something you could always do to accomplish this. But I'll give you the easy way of approaching it, but most certainly there's a lot of ways to go about this. So just please recall the empty string epsilon has length 0. But remember, a DFA will either accept or reject upon reading its input. But this string has length 0. So what does it do then? So what's it do? So no transitions will occur because it's not, there's no symbols to read, right? So question, I want to accept the empty string. What's one thing I can do for a DFA? If no transitions occur, any suggestions? So remember, what's happening is I give you the DFA. It starts in the start state, and then it doesn't do any transitions, and it either is going to accept or reject what state, depending on what state it's in. What's something I could do to ensure that epsilon gets accepted? Now, I'm not saying that it won't cause any other issues if your other strings rely on this state or something, but I'm saying that this is something you can do. Well, think about it. Since it does no transitions, because there are no symbols, right? It's still in the start state, right? So what can you do to that start? Like, what should be included in the final states? What should be included in the final states? Correct. You're correct. That's exactly it. Exactly it. You make the start state a final state or accepting state. If you make a start state a final or accepting state. Boom. So if you ever need the epsilon to be accepted or the empty string, just keep this in mind. This is one of those edge cases with the DFA. So you have to be careful as well. If you put the final state actually just straight up on, you make the start state a final state, you have to watch out, because if you're trying to expect a string that isn't actually the empty string, be careful for that, okay? So if you don't want to accept the empty string, don't make the final state a start state, okay? So just be careful with that. Now, let's consider another example. So let's head over here. So remember that when we talk about DFAs, our goal typically is to accept strings of a language. Previously, we talked about the language of binary strings that have an odd number of zeros. You could describe this formally. You could do this with all sorts of languages, and that's expected, right? If you can mathematically formalize it, you're generally fine. The question is, can you design a DFA that does that? So, just as an example, let's consider another language. We're going to try to design a DFA for a given language. Suppose I want to design a DFA that accepts strings of the following form. They're going to be x, 0, 1, y. So x and y in here are any strings of zeros and ones. So this string has a very particular form. You can also describe it in a different way. Here's another way I could describe the same set of strings to you, or language to you. It's W, and I must stress that we're going to be talking about the binary strings. So it's going to be a string such that W has the form x0, 1, y for some strings consisting of zeros and ones. So these two are actually just two different ways of describing the same set of strings, the same languages. So sometimes it's helpful to think about one language and be like, okay, well, what does that actually mean? Well, it looks more like this. So this is more like the form you might be more familiar with, where we given the string, it has some alphabet, and this is what it would look like. So you might think of, damn, what the heck is this? Like, what does this look like? Well, actually, what we're actually describing with this example is trying to detect a substring. So for those that aren't acquainted, a substring, if I give you a string, a substring is a string that is found and contained within another string. So in this case, the pattern for the substring is a 0, immediately followed by a 1. So any string that has this pattern in it is in this language. That's what this says. So what we're trying to do is actually detect binary strings that have this substring. So we're trying to detect the substring 0, 1. So if we can do that, we're okay. So the minute you identify that is as follows. So I'm going to give you a common trick for how you might deal with something like this. So here's a common trick. Not saying that this is what you must do, but this is most certainly a trick. Is contain a path. So we're going to make a pathway in our transition diagram. Contain a path with the substring. Where other transitions on states are used to manage exceptions to the substring. That is, remember, all we need is just to encounter the substring, and then we're okay, right? We just got to make sure that if we run into anything else after the fact, that we're not interfering with this process of detecting 0, then 1. The minute you see that, this becomes actually a pretty easy task. So, since the substring actually has only 2 symbols in it, I'm going to make an initial start state, Q0. And then what I'm going to do is because remember, my pattern has 2 symbols in it. So if I'm starting in Q0, I'm going to need 2 more states. One for upon reading a 0, and then another for reading 1. So this might be a natural thing to try. So Q1, Q2, but you know right away that I'm going to need that pattern somewhere in here, right? It has to go 0, then 1. See, 0, 1, there's my substring right there. So if I can get from Q0 to Q2, I'm good. But remember, there's all sorts of other stuff that can happen too, right? So I have to be careful. Also, another issue is strings that look like this. All this stuff doesn't really matter. The point is that 0, 1's right here. That's the first time we run into it. But the thing is, there's a whole bunch of zeros that come before it. Do you see that? So I need to make sure I take this into account as well. So notice that whenever I read a 1, that's definitely not reading 0, 1, right? But the minute I see a 0, I got the first symbol for the substring. So that's the first symbol, right? But I may be potentially reading in more zeros. So I'm going to include a transition when I read 0, like this, until I potentially see a 1. When I see that 1, then I've read the pattern. But anything after that can happen, right? I don't really care whatever stuff comes after. There's just a bunch of... It doesn't matter what's after this, right? Does everybody see that? So here's a DFA that actually does it will recognize this language. But yeah, no. So you'll notice quite quickly that so this will just read in the 0 and 1, and it will able to be handling more symbols if they were to appear on the left side of it and the right side of it. Are there any questions about this example, or is this pretty darn good? So this is a common technique you can use with a DFA, is you embed the pattern in your DFA. So you make a pathway, you contain a path with the substring where all of the transitions are handled such that you're ensuring that this pattern gets read if it is going to successfully get here. Think about it like an obstacle course. So let's take this idea then. I don't see any questions, so let's proceed. Let's take this idea and just drag it to its more, a different kind of application. But it's very much the same idea. So let's consider, in one last example, let's try to compute, sorry, not compute, I get really excited about this because you could take all this stuff and think about it in all sorts of different ways. But when we think about automata like this, I would like to design the DFA such that it recognizes the language, but I always like to take advantage of the internal structure, the specific or particulars of that language. Just like when you try to solve a problem at a higher level, for a problem, I design the algorithm to exploit the properties of that problem. It's the exact same exercise. So let's consider another one. Let's consider, so I'm going to call this at least 3 ones. So what I want to do is I want to come up with a DFA. So let's design a DFA that recognizes binary strings with at least 3, well, I'll write the word because it gets a little bit strange when you don't, 3 ones in them. So just to be clear, what I mean by this is that a string like this, that's okay. A string like this, that's okay. A string like this, that's also okay. All 3 of these are okay. However, this string, not okay. Having 2 ones and a 0, that's not enough ones for me. A string like this, there's no ones in this. Not okay. We need to reject those. Is that clear, everybody? So we're going to take the same idea that we had previously. Remember, we can almost think of the same process where we have our target of I need at least 3 ones. But you can think of it like I need to detect 3 ones, but now I don't need them to actually be in the case where one has to immediately follow the other. It's just that they have to appear. So you can think of it like a loosening of the same design strategy. So here we go. So you could use the same idea. So I have at least 3 ones, so I'm going to make a pathway with 3 ones, because I need at least 3 ones. So I'm going to make a start state, call it Q0, Q1, Q2, and Q3. If I can see at least 3 ones, right, then I'm good. Doesn't matter whatever follows after that. As long as I see those at least 3 ones, we're okay. So I have a question now. I haven't entirely defined the transition function though. I just told you that if you see a 1 here, you go there. If you see a 1, you go there. If you see a 1, you go there. I'll give you a bit of a tip here. Let's see here. Let's see. The final one, remember I just told you I don't really care what happens after here. But what should I do for the transitions on Q0, Q1, and Q2? Any suggestions on what I should do with these 3 here? Because I need to define a transition when I read 0. Do I do something quite like that over there, except I don't have a 1 in there? Because remember, for each symbol, I have exactly 1 defined transition on a given state. I can't have multiple ones. I can't be in Q0 and Q1 at the exact same time. I can't do that. Well, remember, I only care about the 1, so if ever I see a 0, I just stay in this current state, right? And boom, there you go. So notice that if I try any one of the strings I have over there, notice that whenever I see a 0, it doesn't matter because it doesn't accumulate our count. You can imagine going along this pathway is like keeping a count of how many I've seen so far. And this is, you'll notice quite quickly when you're dealing with a DFA like this, since the only thing we know at a current time is the current state, we have limitations for what we can remember. We have a limitation of memory. We don't have any other place to put things, so we can use states to help us remember where we are. But remember, there's a finite number of them. So just keep in mind, actually, I'll just summarize what we just did here, just to give you an idea of how this all came together. So the design idea here is we have a path of vertices where each is a state for when one symbol 1 is read. So naturally, the path is of length 1, 2, 3. The path has length 3. Length 3. So at least 3 1s are read. Then we permit any other symbols. Right? Now I have a question for you. So now that you understand how we could do this with at least 3, what would I do if I wanted to have at least 4 1s instead of at least 3 1s? Are there any suggestions for what we can do with this? Any suggestions at all? And you don't have to get very particular about what states there are or anything like that. Just tell me the big overall concept idea. So remember, all I had here is I have a path of length 3, each one with 1s on them. This guarantees I'm going to have to read at least 3 1s to get over to Q3. So what would I do if I wanted to get at least 3 1s? Sorry, at least 4. At least 4 1s this time, instead of just 3. I would do what? So in our idea is I have a path of vertices or states. Yeah, add another one, exactly. You just add another state in here. You just put just jam it right here. And you're just like, I'll call it Q blah. Put 1 there, put 1 there. Put a loop here with a 0, and there you go. This will accept binary strings with at least 4 1s. Very nice, very nice. So these are a few examples of designing DFAs. I must stress, remember, we have not proven that these DFAs are correct, but most certainly I find that when you describe the DFAs, especially when you describe them state by state and the reason why they're there, it's very helpful for informing somebody why it's designed the way it is. This isn't the same as mathematically proving that it is correct, but most certainly it's intuitive. So that's all I have to say about DFAs at this point. So I say thank you so much, everybody. That was DFAs, at least at a high level. So are there any questions at all about DFAs? So now, based on the vote I got in the chat, we're going to hold off on the discussion, because next time when I come back, I'll talk about what regular operators are, because you know I talk about regular language. I didn't tell you what that means, what regular means. So I'll tell you a little bit about regular operators, so it gives you some intuition, and it'll be coming back to some more string-based discussion. Then we'll talk more about DFAs again, but we'll talk about them at a lower level. So we'll talk about how a DFA actually works. So how, like, you know, I talk about the tape and moving the tape like that, or going from one state to another but on a read. There's a formal mathematical way of describing this process, and this will be useful when you actually prove that a DFA is correct. So if there aren't any questions, I don't see any questions in the chat. A couple of things before I go for today, because I'll head out, is I would say thank you so much for coming on by, whether you're watching this in the future or you're watching this live. It was a pleasure to have some fun in the chat with everybody, especially talking about DFAs. This is always an exciting topic. I think it's a good kind of invitation to talking about models of computation. Most certainly, it's kind of the stepping stones for starting up, because remember, in a DFA, we don't have any like extra memory. We just have the states and transitions. All we can remember is the current state, right? So different models of computation build on top of the DFA and other equivalent models of it. So when we come back next time, I imagine that's what we'll do next time, is we'll talk more about what that means. And if we have time after that, we might start talking about non-determinism, a whole magical concept in computing. This idea that you can have a computer that's in multiple states simultaneously. That's at least one way you can think about it, that it has this clairvoyant ability to know when it accepts among being multiple states, almost like it's perfectly guessing which transitions to take. It's like magic like that. But the point is that we're going to see a basic form of that if we have time. If not, we'll see that later on in the month. So I'll say thank you so much for coming on out. If you enjoyed this, please like it, tell your friends to come on out and join the fun. Of course, join the fun on Patreon as well. Join on patreon.com/pagewizard. That's how you can get access to the notes. I talked about some examples here today. You can find those in the notes on Patreon. Those will be released later today. And of course, if you want to support your computer scientists outside of academia, not academia per se, but at universities like me, consider supporting there, because right now we need scientists that are capable of doing their research, but can't. There's a lot of issues with the university ecosystem today, and we need to support those academics that are outside of universities. Other than that, I will say thank you so much for coming on out, and have yourself a beautiful day. I'll see you later.